everyone. Thanks for returning to CCN 2021. You are here for a generative adversarial collaboration, in case you didn't know that. I'm Thomas Naselaris. I'm hosting today, and my co-host is Eric DeWitt. And you are here for the GAC, What Constitutes Understanding a Ventral Visual Pathway Function? Ah, there's Jack. Hi. Gotcha. Cool. So this is one of 5 GACs we're presenting this year. We have another coming up on September 23rd and August 1st. And we have one more keynote, a tutorial session, which is coming up on September 24th. So I just want to start by presenting the slide of all the speakers and presenters and discussants today, to thank them for participating. I'll just explain the ground rules briefly. Every presenter will talk for 5-ish minutes, and then we'll have 15 minutes of discussion between panelists and the audience. And the organizers asked me to communicate their preference for spoken questions. So if you have a question or a comment, you want to become part of the conversation, we encourage you to raise your hand, and Eric and I will give you a chance to speak. We'll unmute you. You won't be seen, but you'll be heard. Of course, if you don't want to do that, you can enter your questions in the Q&A box. Any other comments or chatter should go into the chat box. Any other notes to communicate? Well, if not, I will turn the screen over to Carlos Ponce from Harvard Medical School, who will provide an introduction. So I'm going to stop sharing, Carlos.
All right.
All right. And why don't you load up your screen?
Sounds good. Well, welcome everybody. This is, I am thrilled to.
Oh, you're suddenly muted.
You're muted after you got thrilled.
Let's see. You're muted, Carlos. Yeah, give it another
How's
shot.
that? Am I up?
Yeah.
We can hear you.
We can hear you. We just need to see your screen again.
Got it. Okie dokie. Great. Well, thank you all for being here. My job here is just to get started with a little gentle introduction to the ventral stream, and again, to thank you all for being here. So yeah, the topic of today's discussion is the ventral stream, which in primates, as you all know, corresponds to a network of cortical areas along the occipitotemporal lobe.
Sorry, Carlos, can you full screen? You're going to slide presentation mode. I
Sure.
think they're showing up as a little. There we go. Thanks.
Is that good? Okay. And yeah, this is an area that is concerned with form and object recognition. Most of what you'll hear about today comes from monkeys, but there will be some data from humans as well. So this is a story about the ventral stream, what you'll be hearing about, but it's also really a story about us, all of us who really want to not just create data and research findings about the ventral stream, but also synthesize it into a story that can answer basic questions like what evokes responses in the ventral stream, how do populations exchange information, and importantly, what use can come of this knowledge? Where is the deliverable that we're going to create for the individuals who pay for our research? So the format of this is generative adversarial collaboration, which means that we were tasked to create camps for understanding. And I created this little schematic to highlight that although we were able to identify certain specific themes and camps to thinking about the ventral stream, we wanted to make a distinction between the fact that you have the camps, but individuals, everybody here, every participant likes to make use of every tool that is available to them to understand the ventral stream. And so therefore, individuals will bounce between different camps, but I think it's also fair to say that some individuals are much more comfortable with some specific camps than other individuals. And I think you'll see some of those contrasts come in this format. So to explain these camps, the structural camp, the semantic camp, and the sampling, which is, by the way, how I started thinking about this whole thing, but you'll see more nuanced views of this. It helps to go back to the very first story, one of the early stories of understanding the visual cortex in the 1950s, with Hubel and Wiesel when they set out to understand the first stage of the ventral stream, primary visual cortex. So these individuals didn't have a lot of tools. They started with Steve Kufler's modified ophthalmoscope and later a projector that was able to create simple stimuli like spots or contours at different rotations. And armed with these tools, and also with David Hubel's recently developed microelectrode, which allowed them to record for spikes from individual neurons, they were able to find not just the specific part of retinotopic space that elicits responses from neurons, the location of the receptive field, but by engaging in this item process, where by hand they drew the specific state of the light patterns in the center receptive field of the highest intensity. And by doing this across. So by doing this across multiple sites, they were able to draw enough receptive field shapes that it gave them the opportunity to synthesize their knowledge, as we'll now see primary visual cortex as an orientation tuning map, although there's obviously more things that we can think about primary visual cortex. So this is a very clear story, I think, to most of us. It's a story that we all learn about coming into studies of the ventral stream. So our first camp, the structural camp, is one that I think as the efficient or idealized version of this Hubel and Wiesel approach, where an investigator begins with the idea of, okay, we have a conceptual space like orientation or head-body ratio. Then the investigator instantiates this particular theory with a set of images representing different values in the parametric axis, and then measures the responses of neurons as a function of this parametric axis of this set of images. And so the story then can conclude that a neuron is signaling value, a value in interpretable parametric space. So this is one particular approach. The problem is that as we move on to different parts of the ventral stream, one begins to find that there are neurons that are responding to less simplified, less parameterizable objects such as this. And so there the question is, how do we handle this large, very large group of complex images that neurons may be responding to? And an individual that stands closer to what we're calling the semantics camp might actually leverage the fact that we already have large, very pithy and useful ways to describe lots of images in the world using categories. We have language, we have semantic concepts. So we can create stimulus sets that correspond to things like faces, places, and bodies, and then relate neuronal function to those categories. And this has been a very successful approach as well in understanding of the ventral stream. Now, one advantage of the semantics camp and the structural camp is that they can make use of this easy to communicate semantic concepts to organize understanding. So, you can assign images to faces or places or the specific categories, or you can assign images to numerical axes, which themselves can be understood as with simple words like orientation, head-body ratio formulas. But there's another camp, the sampling camp, where individuals might think that neurons really are just signaling learned visual attributes. So for example, a neuron through experience might learn to encode specific combinations of visual attributes like color and texture and shapes. And these attributes simply may or may not align along anybody's thought parametric axis or any semantic categories. And one example of how this can really work are convolutional neural networks, which through a process of trial and error can learn to specific kinds of filters in their hidden units that can become useful for the diagnosis of an identification of specific categories or other kinds of tasks. Ways of understanding and extracting these visual patterns from neurons, as you'll hear about today, used by convolutional neural networks that can be fitted to neuronal data to create a substitute network model of the neuron. And then one can use gradient descent, kind of the deep dream approach, to synthesize the image that best stimulates any one of those units. Or you can also use pairing ventral stream with image generators like GANs or vision transformers in a real-time closed loop design. That's what we're called X-Stream. That also helps without necessarily having a model in the middle, extract information encoded by neurons in the ventral stream. So these are major camps. Like I said, this is about to get a lot more nuance coming with Ed and other folks coming later. But this is just one way to start to think about one key problem here in ventral stream studies, which is what do we owe each other when, for example, an individual or set of individuals in the closer to the structural camp identify axes that are important for understanding neurons. Folks coming from a sampling camp identify visual patterns, the shapes that are also important. Is it the job of the person in the sampling camp to try and fit these images onto the standing axis? Or is it the job of the person with the axis to try and explain these images? And how do they relate to other concepts like semantics? So this is just one of the many problems that I think we'll be exploring and revisiting. But that's it. So this is just a gentle introduction to the problem. I actually don't need much more the 15 minutes for questions. So unless there's any burning questions, I'd like to hand the microphone over to Ed.
Okay, thanks, Carlos, for a wonderful and indeed gentle introduction. Let me share my screen. So unlike Carlos, I am not going to try to divide all of Gaul into 3 parts here. Here's where my thinking about this GAC starts out. So I'm going to be mentioning what you could regard as camps or other things, but I think it's maybe a less complete organization of the universe than Carlos gave. So the title of our GAC is What Constitutes Understanding of Ventral Pathway Function. I think in this forum, this is a question for neuroscientists, even though I think philosophers could really clarify what neuroscientists consider to be good explanations or good understanding. And that's why Carl is here. But neuroscientists kind of matter because they're the ones that get to spend the millions of dollars, and they're going to offer the explanations that they think are worthwhile. Can everybody see enough of my screen to see this slide good? So for neuroscientists, I think the question cashes out to what empirical endpoints do we present in our talks and papers with at least the implied claim that they tell us something new about how the brain works. You can see in the slide I've highlighted in neon pink how the brain works a number of times. And for me, this is the phrase that should be uppermost in all of our minds. We should be trying to learn something new about how the brain works. And for me, that should be a major test of explanation or whether we've added something. So I'm going to list 4 types of endpoints that I think are very different. And the debate we could have about them, I think points for debate include how do different endpoints compare an explanatory value? That is, to what extent do they tell you something new about how the brain works? How do they conflict in explanatory approach? Because I think most talks and papers at least imply that other approaches fail to explain how the brain works, or at least fail to explain as well. And finally, and this to me is the hope and promise of this GAC across the coming year, how can they be potentially synthesized or reconciled to increase their explanatory value, their mutual explanatory value, and decrease explanatory conflicts, which always seem to go on forever. That is, how can adversaries collaborate to explain more about how the brain works? So in the following slides, I'll list 4 types of endpoints that I think differ in explanatory value. I think they conflict in explanatory approach, and I think they are amenable to synthesis. I will draw all my examples from area V4. It's convenient. There are other people here that study V4. And because it's sort of an intermediate stage in the ventral pathway, it's amenable to many potential explanatory approaches. So the first explanatory approach I've listed is featural models. I think that featural models explain ventral pathway function as input information filtering by neurons, and that filtering in those models is expressed by mathematical functions. And this happens to be a very old example from Jack's lab of a function, a two-dimensional function to explain the responses of a single neuron explain and predict the responses of a single neuron across many images in terms of the spatial frequency and orientation content of those images. Then structural models is something that Carlos referred to. My definition here, I think, may be more narrow. For me, structural models mean models that refer to the structure of the thing being represented in the brain. That is, representation of the causal physical reality that produced the information transduced on a sensory sheet. In olfaction, you could regard the causal physical reality as the molecular structure of odorants. In vision, I think of the geometric structure of objects and scenes. Again, these can be expressed by mathematical functions. Here's a recent example from our lab that I won't bother to explain, but in the end, we think we're able to explain and predict the responsiveness of V4 neurons to particular three-dimensional shapes in terms of a model based on the geometric dimensions of three-dimensional shapes and expressed with plots that are slices through about a 12-dimensional tuning range. Then something that's becoming newly popular as an endpoint in high impact papers, and I'm looking here at Marge and Jim DiCarlo if he were here, using images as an endpoint. That is, and frequently CNNs are used as a means to generate those images, and frequently the responses of individual neurons are used as the metric to evaluate those images. So I think images again explain ventral pathway as input information filtering, but now the type of information that's being filtered is expressed by extension of the high response stimuli, and in some cases, semantic interpretation of those stimuli. And then finally, CNNs are frequently, I think, an endpoint for talks, papers. Certainly the endpoint that the brain score competition run by the DiCarlo lab aims at. I think CNNs explain ventral pathway function as transformation of input information into behavior, and the form of that explanation is a functionally equivalent artificial mechanism with a specific architecture. So this is also now a slightly older paper from the DiCarlo lab. Dan Yaman's the first author, it's 2014, and they're using various kinds of artificial networks to build predictive models of V4 and IT neurons. These are results for V4 showing that the most successful predictive models were those that used sets of artificial neurons across an entire layer of approximately 6-layer network as basis functions for linear models that would predict responses. And the most successful models came from neurons in intermediate layers of an AlexNet-like network. Okay, so So that's my list, which may have ruffled some feathers, and it's not meant to be exhaustive. It's just examples of endpoints that I think we present as, here's your answer, we're done. They, sorry, somebody just knocked on my door and distracted me. I think they do differ in their explanatory value, in their approach to explanation. And yet I think we can talk about how to unify or synthesize across these models. Most GAC competitions, I think, compare variations within one of these explanation types, which makes sense because you can use the same metric. But then you're making an a priori choice that a particular kind of explanation type is what makes sense. You're not moving outside of that. In this GAC, what I hope is that we can compare and contrast and synthesize across these explanation types. And I think that's harder. There is no single metric. They use different metrics, and they differ in the very notion of what constitutes an explanation. So I'm going to end there, but to start off a debate, I'm going to throw out some incendiary comments about each of these types of models that may provoke reactions and debate from people. So here are my incendiary comments regarding featural and structural models. You could say that predicting how neurons respond doesn't explain how the ventral pathway works any more than predicting when valves open explains how an internal combustion engine works. With regard to images, you could say the best stimulus images for driving neurons don't explain how the ventral pathway works any more than the best gasoline for driving pistons explains how an internal combustion works. And with regard to CNNs, you could say that replication of brain function with a computer doesn't explain how the ventral pathway works any more than replication of car function with an electric vehicle explains how internal combustion works. And I'll leave you now to react to those or to anything else I've said. And I will. Shall I stop sharing screen, or does anybody want to refer back to one of my slides?
I love this slide, Ed. This is an awesome slide.
Yeah.
Thanks, Jack. Partly done with you in mind.
If we agree with you, then can we just go home now?
That wouldn't be a very fun result, though.
Okay, so let me start with my first question. As somebody who's still pretty new to the field, believe it or not compared to some of the younger guys here. But one of the things that I found very, very compelling about CNNs and about the image approach is that, I share with Jack the idea that our goal is to try and understand the ventral stream, how the brain works in the context of the natural world. Now, CNNs do really well like that. And even image-based approaches can help us in that direction. So the question with featural and structural models, and I'm not 100% sure about the distinction between the two yet exactly, so I apologize. But how do those models, they could give us some understanding about the brain that is kind of local, right? But how do we know that it's telling us something that is going to be of use when trying to understand the visual world in general, like any random image? Is there a way to extend that?
I'm not entirely sure I followed that, Carlos. It seemed like you went from CNNs to images.
Well, yeah. Well, to me, they're sort of similar in that, and I'll elaborate now how images do allow us to understand neurons in the context of natural scenes. That's something that I think is very important. And when you presented some of those parameters, like the idea of the structural slide, and you had an interesting set of visual stimuli and how one's able to explain the responses of E4 neurons to that set of stimuli. I agree that that's a form of understanding, and it has great explanatory value. But the question is, how does it generalize outside of that specific stimulus set?
So Carlos, my hypothetical starting point here is that nothing has been explained. So I'm challenging you to say about an image or a CNN or anything else, what has been explained and how. Basically, what new thing have we learned about how the brain or how the ventral pathway works?
Okay, I'm looking around here to anybody who likes CNN. I have an answer, but I don't want to hog this.
Well, it's hard for any of us to respond given Ed's last slide, because Ed's nihilistic slide basically says you can't explain anything ever with anything. And so, why bother?
Yeah.
Carlos,
Which
can
may be
I
true.
ask you to clarify your question? So you seem to be conflating two issues. One is, even with a structural model, you could set up an image computable version of it and still predict responses to stimuli across the board, whatever stimulus you want. So as long as you take your structural model and make it an image computable model, then with every model you can predict responses and assess whether they're good or bad. So could you explain then?
Yeah.
Assuming that you have an image computable structural model,
Yes.
then
so,
what is your question?
So the question is, so I think of CNNs as the image computable model. So can we, what would be the good competitors on the structural side as to CNNs?
So we would have to, if you want to think about an Hmax model, for example, and build a structural curvature model based on an Hmax model. It's true that there aren't good image computable models for the structural aspect. We're still trying to understand what structural features represent the response as well. But one could imagine that if push came to shove, we could set up an image computable model that could represent these structural features.
Mm. And the path there is to understand what the structure is, what the structural features should be.
And that's what many people end up focusing on.
I wanted to ask a question to Ed, because can you please give us an example of what could be an explanation that is satisfactory, and then we can maybe come up with how CNNs could be formalized in that way?
Sure, I will. So I think I'm glad that I'm providing amusement value for Jack in this GAC discussion. So I think my incendiary comments all point out the fact that everything we do is a little bit like blind men feeling different parts of an elephant. And to go back to the internal combustion engine as an example, if you really wanted to understand how it worked, you would have to understand how pushing the throttle injects gas, how opening the valve to admit oxygen and sparking the spark plug. You would have to understand the system from front to back.
Can I make a small comment here just to clarify myself? So when you say to understand this, to that, it's basically you're suggesting in some way in my head is that in every step, build a small model and predict what's going to happen. Is that different from what you're saying? Because
so here's what I'm saying. Let's imagine that we have a CNN that works exactly like the brain does. Then I think the great thing about CNNs, I think the untapped potential of CNNs is that you can do a dream experiment on a CNN. You can measure every activation level, every connection weight, every influence of every signal, starting with layer 1 all the way through layer 6. The explanation is there. And I think there are ways of reducing and presenting that information. And I've started doing this. And I could refer you to the paper from this year as a prototype example. So you could explain how a particular pattern of activations of Gabor filters in layer 1 eventually leads to the activation of a unit in layer 5 that winds up being the most important driver for the solution that you're looking at a pussycat. If you could do the same thing in the brain, terrific. You can, but what you can do in the brain is pieces of that. So you can look at how information from one area, say V2, gets sent, routed to different modules in V4 and how it's transformed as part of that routing. So I would say that the kind of explanation you would need to understand the ventral pathway the way that you understand an internal combustion engine already would be knowing the entire flow of information through multiple layers, how things get thrown away, how things get transformed into other things. Eventually, you have to move from an image, which is a worthless array of millions of numbers, to explicit signals for the kind of things that we care about, that we can talk about in the world, like the structure of objects, the structure of scenes.
So I think I mostly agree with you, but I think I would want to push back a little bit about this last point that you make about explanation kind of ending up about things that we can explain to each other. Because I think I'm not part of the image camp, because I think it was a little bit mischaracterization, maybe in some sense, of the end point of some of the at least our paper in Science about the images, because the end point there was the model that was driving those images. But regardless, I think this idea that, like, so CNNs, to me at least, have that all of the pieces, as you mentioned, like, can be basically like be studied as mathematical equations going from images to the final neuron, and you know, making the neurons fire in certain ways. You can predict them. I think that to some degree, I feel like that explanation, that is the explanation, because the other explanation, which is what we can talk
hang on, let me clarify. When you say that is the explanation, you mean the CNN is the explanation?
Yeah, so I'm trying to make the point that at some level, I feel that the CNN has to be the explanation that we seek, because otherwise, for example, like in 300 BC, we could be talking to some person in some language that is not accessible to them. And today that person will be saying like, oh, I understand, you know, curvatures, but 300 BC, nobody knew what.
I think it's important that we recognize that we've run out of the 20 minutes for Ed's allotted time. I expect that we're going to be coming back to explanation is clearly at the heart of this discussion, and we're going to keep circling back to these issues. So I suggest that we put them on the side and move on to our next speaker, if that's okay.
Sorry, thank you.
That's Jack.
Yeah, this issue is going to keep coming up over and over again. So we'll have a lot of time to talk about this issue, because this really, I think, lies at the heart of what's going on these days. So I originally was going to just talk about explanation. I'm going to talk around explanation, but I think where I'm going to end up, I don't know, may not be satisfying to some people. I do want to say that, you know, Ed and I love arguing with each other. We've been doing it for decades, but we generally agree on things. And I actually agree with what Ed said. Right. Oops, I don't know where that came from. Okay. So, you know, let's just take a step back and figure out what we're trying to do here, right? It's science. What are we trying to do? We measure some stuff. We build a model of the stuff somehow or other. Don't worry about that yet. And then we use that model that we built of stuff to predict new stuff, completely different stuff, hopefully, because we want the model to generalize and to explain everything. And of course, the goal here is to predict as much stuff as we can possibly predict. And really, that's what the government's paying us for. The government does not care about our explanations. Let me make myself tiny. The government doesn't care about our, wait, I've got it here somewhere. Here we go. The government doesn't care about our explanations. The government wants us to be able to predict things in the natural world so that they can do work, right? I mean, the work comes in the prediction. It doesn't come in the model. The model is a way, is a method that allows you to do work. And having an explainable model that's understandable means that when the self-driving car hits a pedestrian, you don't, and the lawyers come to you and say, why did the self-driving car hit the pedestrian? You can actually explain why that happened rather than saying, oh, my CNN did it. I have no idea, right? So really the goal is to come up with the simplest explanation possible, the most elegant explanation possible that predicts as much as possible. That's really, I think, what we're trying to do here. And I don't think anybody's going to argue with that. Now, the question is, okay, given that that's what we want to do, how should we prioritize our workflow to make sure that we do that? And I have argued for a long time, forever basically, that the first thing you need to do is to make sure that the model predicts. Because, you know, trying to adjudicate between models based on, say, statistical significance is a fool's errand, because you're basically in that scenario, which is the most common scenario, you're trying to adjudicate between models that are merely exceeding chance performance. They're not. That's a poor way to try to compare models. What you want to do is compare models in terms of their ability to predict out of set, where out of set means out of the set of stimuli and tasks that you used, and out of the set of subjects that you used, if you're either a primate neurophysiologist or an MRI person. So the first thing is it has to predict. If the model doesn't predict, then all bets are off. The second thing is you want the model to generalize to naturalistic stimuli. Doesn't matter what regime you used to build your model. It does not make any difference. But in the end, the model has to predict naturalistic, the natural world, which means, you know, for vision, it means movies and eye movements and stuff like that, right? And finally, the model has to be elegant. You want the model to be elegant because an elegant, simple model is going to be easier to understand, and it's going to be easier to explain, and it's going to provide more intuition about what's actually happening than a complicated model. But you notice I'm putting this as the third priority, not the first and second. The first and second are get in the right space. Like first get in the right space. Make sure your model is is near the optimum, or as optimal as you can make it, and then worry about making it elegant. I would argue that that's the order that things should be done in, and you will see that I'm going in the direction of CNNs as being very useful intermediate tools in building an explanation. So the main thing we're arguing about in this weird debate format is what model framework should we choose, right? And everybody's got all these different names for model frameworks. I don't even know what they mean: structural model, semantic model. I know what an ANN is. And if all we tried to do was focus on the first two priorities, which are prediction, performance, and generalization, we would probably pick an ANN, because an ANN, artificial neural network's a universal approximator. It'll fit whatever the heck data you have. It'll work great. You'll be all set. But the problem is, and we all have to acknowledge this, that on the third priority, which is having an elegant model, ANNs fail miserably. First of all, they violate the fundamental principle that your explanation should be of lower dimensionality than your measurements. In fact, the reason ANNs work is that the dimensionality of the ANN is higher than the dimensionality of your measurements. That's not a solution to a problem. That's a different problem that needs to be solved. We need to make we want an explanation whose dimensionality is lower than our measurements. Otherwise, it just becomes an overfitting exercise. So we got to do that. And then, of course, the third thing is that ANNs don't have any, easy interpretation. You can't. Yeah, you can talk your way around it, but as we all know, who have tried to figure out why our NN is doing what it's doing, they don't have an easy interpretation, and they can be frustrating. Now, as an aside, I should mention that there are other ways to use ANNs that might be that are not commonly used, but I think will become more commonly used, that overcome some of these problems, and that is basically leveraging the power of the modern ANN fitting software stack and modern GPU hardware to build biologically realistic or biologically constrained, biologically informed artificial neural networks. And that you can do that. We have a project that after like 10 years is about to, I think, finally be submitted, that essentially builds a stack from V1 up to V4, where all the modules in the stack are biologically plausible modules that have a very clear computational interpretation, but they are implemented in terms of just modern ANN architectures. So I think that's a good, balancing act if you want to do that, and I would encourage people to do that. I think very useful. It allows you to use exploit the power of ANNs while maintaining interpretability. But I would not argue that you should do this alone. In fact, I wouldn't argue that you should do anything alone. I am a let 1,000 flowers bloom kind of guy, and my sort of fundamental assumption is that everything we know about the brain is probably wrong, and you don't want to get too caught up in your theories. And so I would prefer personally to test as many theories as possible, as rapidly as possible, and sort of treat this as a data-driven exercise. And in that case, the idea is to just stack all the models on top of one another. So you have a semantic model, fine, stick your semantic model in there. You have a structural model, stick your structural model. You have 5 structural models, stick your 5 structural models in there. You have an ANN, stick your ANN in there. Fit them all simultaneously, then take the predictions of all of those individual models and let the data tell you which model fit well where. And in a lot of brain areas, a lot of neurons, multiple models are going to fit. But if you have a good software stack and a good statistical framework for fitting models, you should be able to do this. And we've published a lot of papers and a new tutorial, I should have put a link to it up here, on this banded ridge regression framework that is essentially an implementation of Tikhonov regression, which is a classic regression framework, but optimized for neurophysiology and fMRI workflow that allows you to fit multiple models simultaneously. And you can fit thousands and thousands of parameters and dozens of different models using this framework. And the data will tell you which model works best for your neuron or your voxel. And here's just an example of this. This was actually from a driving experiment. Subjects were in virtual reality. This is human subjects. They're in virtual reality. They're driving around a town. It's a big town. It takes about 10 hours to learn the town. And then we take the data set and we fit models to it. And this is 30 different models. Some of these models are semantic models, like gaze semantics is the semantic category of the object you're looking at. Other models are computational models that have to do with optic flow, or an underlying navigation model that's drawn from the neurophysiology literature. You can also fit a neural network to these data. And the data will just tell you which of these models fits in the different brain regions in every single voxel, or if you did this with neurophysiology, in every single neuron. So there's no reason to actually have this argument. We don't have to decide what model framework to use. Just fit them all and let the brain tell you what model is the right model for each area. And then if you find out that you have, say, a neuron or a voxel that you can only fit with a semantic model, and you don't like semantic models because there's no mathematical algorithm that gets you from the world to that model, you have to have a human in the loop, which we all know is a bad idea, then you can focus on that specific semantic model and try to basically build a computational algorithm that will give you that same data. That's it. Thanks.
I noticed that there are 2 thoughts. There's one in the question and answer from Nicholas Kriegskorte. Nicholas, do you want to ask your question? Weban? Okay.
I think he has to be promoted to the panelist to ask it.
I see. Why don't I read it out loud?
Oh, here it comes, I think.
Does that work? I don't see the tension between these 4 different approaches. They seem to be different pieces of the puzzle. Ultimately, we need image computable models of the information processing that explain both neural responses and behavior. Feature and structural descriptions provide a step of abstraction from the data, which constrains brain computational models. Useful. Superstimuli and controversial stimuli provide a way to make bold predictions about responses far from the training population on the basis of brain computational models, thus providing severe tests essential. What's the problem? Question mark.
Yeah.
Well, that was kind of my argument. So,
Okay. Well, then I'll respond to both. I think that a CNN by itself, without any further use or interpretation, for me is not an explanation, because you can show me the CNN, you can show me its performance behavior, but I haven't learned anything new about how the brain works. Then I could point to other endpoints where I feel like I have learned something new about how the brain works. So harking back to Jack's example from V4 and Carlos's example from Hubel and Wiesel in V1, the discovery of orientation tuning does tell me something new at that time about how the brain works. I know that one of the very first things the brain does is extract information about local orientation and spatial frequency. So that's the difference. And I think that difference exists between the four things that I talked about. It's,
Yeah,
again, it's the operative phrase for me, and I think that should be for everybody, is what new thing have I learned about how the brain works?
So
yeah, the bottom line is that explanations are good explanations are subjective. We, as the community of scientists, have to decide what a good explanation is. Predictions are objective, but what is a good explanation versus a lousy explanation? That's for us as humans to decide. And I agree with Ed that, you know, I actually think Ed's statement about just evaluate whether you learn something about the brain is a really nice kind of way to determine that.
Yeah, so, and
humans are low dimensional, right? We want a low dimensional explanation.
Yeah. And I think Jack and I agree here, just not on the order. My feeling is that your choice of how to model is going to determine the intuitive explanatory value, what Jack calls the elegance of the model from the start. Jack feels that if you make prediction king and let everything fight out on the prediction level, then you take what you've got and make it elegant enough, intuitive enough to provide an explanation. So that's a difference in approach that I think is arguable.
Yeah, but it's just a workflow.
No.
We're basically on the same page.
No.
So I would go ahead.
No, please.
I wanted to add a point. I think I largely agree, but I think it's not just a subjective explanation. I think there are differences in, for example, if you want to answer the question, not just the question, can I predict responses to novel stimuli, but answer the question, how do these representations underlie our ability to do some task, right? When you take that question, your answers will be fundamentally different depending upon the model you use. And during my talk, I'll give you a concrete example where that difference shows up. So I completely disagree that it is a subjective explanation difference. It is, I think it's a concrete understanding in terms of how the brain does a computation versus how your favorite network does it. And so there, I think that's where, from my point of view, that's where the difference lies.
Yeah, I would agree. I agree with that. And I don't know if I agree for the same reason. I'm looking forward to your talk. But the idea of the representation, I think, is an interesting way to unify some of these threads and to really find where they conflict. I mean, so Ed, you mentioned that you like the Hubel and Wiesel approach and story. But you know what they did is really they were identifying the representations of a given area. They were finding the shapes of the filters that you say are common to the structural and CNN and a lot of other approaches. So
everything we all study is representation. That's
but I actually mean the shape of the filter, and not some of these networks or some of these theories make different predictions about what the shape of the individual filters represented by neurons are. And
that's true.
CNNs get you there. CNNs help you. The image synthesis approach gets you there. And so those become things that have to be explained as well. So representations at the level of the neuron, I think, is something that is going to make a big difference in future experiments.
I think this need for like this low-level explanation, to me, I think it kind of stems from the idea that like somehow having those explanations will help us as scientists to build the next best model. And I think that is the key thing. And I think to just say that those explanations are the endpoints, I think we're missing something, because I feel like if I just understood in some behavioral English language term what an area does, it doesn't really, at least for me, doesn't really help me unless I can use that understanding to build a better, more predictive model of the same unit that I'm trying to understand. And I think to close the loop is important. And that's where I think all of this kind of like the current CNNs, which are just a base starting model, the semantic and the sort of structural understanding, they can all come together. And if we can formulate all of that as model updates, I think that will be sort of the kind of gradient that we can follow. Is kind of my sense right now.
Well, your second point was consistent with my argument. Fit. You're going to need multiple models because if you have one model, which you could do what Ed said and build. I mean, in fantasy world, you could build a CNN that explains the whole brain, but that's not going to be a good explanation for humans. And so if you're going to build a human acceptable, human interpretable explanation, you're going to need a lot of explanations for different brain areas, and in fact, for different subparts of brain areas.
Go ahead. Sorry, Jack. Sorry.
Oh, it's okay. I thought do you want to say something? No.
I want to add, but I didn't realize you were continuing. Go ahead. Finish your thought.
But your interruption actually made me lose my train of thought. So now it doesn't matter what I was going to say. Go ahead.
Sorry. I just wanted to say to Ko that it is not an understanding in terms of English language, but it's actually.
No, it should be math.
Yeah.
Right. It is. It is.
In the end, it's going to be math, right? The mathematicians always.
And could I add?
I actually remember my second point. Hang on just a second. Okay, so I deal with a lot of engineers, and I know that all the youngsters, everybody born after everybody who came to school after 2012 loves neural networks and thinks we should use them for everything. That's the general rule around here at Berkeley. And all the old geezer professors hate them, and there's a reason for that. Engineering professors want proofs. They want bounds. They want to know, I'm going to build a widget. I want to know when this widget's going to work, and I want to know when this widget is going to fail. And I want to be able to prove that mathematically so that, again, when the lawyers come and sue me for my widget failing, I can explain why it failed, when it failed, and what we knew about it beforehand. And neural networks fundamentally don't do that because they essentially jump right over explanation and go to prediction. And that's fine. They'll give you a great prediction, but now you are missing an explanation. Now you have to take your neural network and, as Ed said in his toy system, treat it as an in silico brain and probe it and simplify it again. And ultimately, a neural network is just not. It's a great tool, fantastic tool, but it's not a good explanation.
So in the service of direct clash, I disagree with Jack that the ultimate goal here is prediction, and that everything else is subjective. There's certainly something in between, which is understanding causal structures. And prediction goes well beyond understanding, being able to make predictions, because we can make predictions for reasons that have nothing to do with the causal structures. Like we can predict measles on the basis of measles spots. We can predict storms on the basis of the way barometers behave. But the spots are not a cause of the disease, and the barometers are not part of the cause of the storm. And what the government, I think, is paying us for is the ability to intervene into these systems and make them behave the way that we want to. And prediction alone doesn't guarantee that we'll be able to do that.
I love that. That's so smart and so awesome. But what I wonder, Carl, is if you have two causal models, how do you adjudicate them if it's not through prediction?
Exactly. I totally agree with this.
Well, there are predictions about what you observe, and there are predictions about what happens under conditions of intervention. I think John Vastola's point here is right on and builds on some stuff that like Judea Pearl and Jim Woodward have said about the difference between causation and correlation. That correlation doesn't continue to hold under conditions in which you intervene on one of the variables. Mere correlation doesn't continue to hold under those conditions.
And let me just expand on Carl's point, which I do think was extremely apposite to this discussion. And that is to say that human understanding of causal structures doesn't mean that it has to be a dumb model. I understand how a computer works, and I can't think of it all at once, but what a computer does is a very complicated causal structure. I could sit down and write down the whole thing. I understand it piecewise. And so I don't think we're condemned to a simple explanation that humans like. I think human understanding of causal structures can be infinitely complex.
Thomas informs me that we're now at the 20-minute point, and so we should move on to our next speaker, I think.
Is that me? I think so.
Yeah, that's cool.
Yeah. Let me. One sec, share my screen. Can you all see my screen? Yeah. Okay. So sorry. So maybe this will give me a chance to like kind of illustrate my position a little bit more. I've been saying some random stuff already. So what constitutes understanding of the ventral pathway is today's question. And I want to start by saying that to me, and this is not such a kind of a novel definition, but like understanding are just falsifiable models of whatever you want to understand. And of course, understanding has different levels. So do I understand my coffee machine? Yes, if I can predict which button to press to give out coffee, that's kind of some level of understanding. But then if the coffee machine breaks, I might need a different kind of understanding for basically like, making the coffee machine work again. So again, so for each of these steps, I think there are specific falsifiable models. And by falsifiable models, I mean models that make predictions that I can test and see. So I can tell which button to press. And then if I press the wrong button, then of course I don't have an understanding of the machine. So that's kind of where I want to start off this discussion. Before I start with what constitutes understanding of what my position is, that I kind of want to dwell a little bit on the why question, because I think the why do we want to understand this might ground us to sort of say specific things about what we might consider to be understanding of the system. And let me lay out 3 different things that I mostly find out from talking to multiple people of why we want to understand the ventral pathway functions. So the first one is basically, it's a complex system, naturally interesting, I'm curious. And these are folks who will say like, rat brain, mouse brain, the C. elegans, humans, macaques, they're all equally interesting, and I'm just curious to understand like the natural world that we live in. So I'm curious. It's kind of the driving factor. And then there's this other form of why, which is I think I kind of like mostly relate to, is like, okay, these areas, they support remarkable set of behaviors which I cannot live without, and I want to know how exactly the brain enables them, hardware and software. And it's like the Feynman kind of understanding, which is what I cannot create and don't understand. And the third one, I think is the most important point, is that they're implicated in neurological disorders. To fix things in atypical conditions, I need to know what typical operating modes are, and therefore I need an understanding. And I think graciously, this is put in most grant applications, but also practically, unfortunately, we probably don't act on this as much as I think we should. So, and the flow usually is like, okay, you need some kind of curiosity to start with, and then you get to the more details of it, and then you kind of like bounce around these 2 ideas of like, okay, I need to kind of build models and then see whether they're implicated in neurological disorders. This is the ventral stream that I think Carlos has already shown, V1, V2, V4, IT, this is of a macaque. And the first approach, which I'm going to kind of say bad things about in a little bit, but now I'm going to first say the good things about it. So the curiosity-driven approach, I think in a caricaturized sense, sort of relies on this question, what drives the neurons in this area? And the what basically ends up being some interpretable stimuli parameter. For example, in V1, it's like the Gabors, V2, it could be like textures, V4 curvatures, IT could be like faces. And I think it's important to point out that this step or this approach is critical to establish the lay of the land. Without this step, we are going to be blindly putting electrodes everywhere in the brain, trying to figure out where vision lies. And so I think it's critical, but I think it won't be enough. And I think people might already appreciate that it's not enough. So what I'm going to suggest as a way to approach this is an integrative benchmark driven approach, where there's testing and falsification of models at every step. So the question that drives the integrative benchmark approach is which models can accurately predict neural properties in these areas. And just a side point, neural properties could be anything. So it's spikes, spike time, spike rates, LFPs, dendritic activity. You talk to some lab, they'll say different things about neural properties. Just a side point, to me, I think these properties can be grounded by using specific behaviors of choice. And those are the things that should tell us which exact neural property should we be building models of. but I'm going to keep that point away for now. And I'm going to say, okay, CNNs, as someone has already, folks have already started saying that these convolutional neural networks currently are some of the best models that predict responses of neural properties along these pathways that ultimately we know are driving at least object recognition behavior. So I want to make the first point that I think Jack already made this. So CNNs are nothing special. They just happen to be the networks that have come up, and also shamefully in some sense from the ML and computer vision. In most practice, of course, they're sort of driven by visual neuroscience in some way, but they're coming up from a different field, and we are basically inheriting them to use them. But they're part of this giant ANN family of models that is still unexplored to some extent. And I think primate brains, at least the sort of the computational form of the primate brain that I'm interested at least in understanding and reproducing, lies in the space which we haven't quite hit yet. And I think the goal of science, at least for me, is to sort of traverse this space while falsifying different models as they come up, and ultimately getting to this space of the primate brains. So there are some points that I want to make. So these models are complicated, or at least CNNs are already complicated. And I want to make this point that the brain is probably more complicated than CNN. So in contradiction to like simple explanation, I think they should become even more complicated. But they're not black boxes. They're not black boxes. And we should discuss this further. I think they're not black boxes because we have access to every equation, every point of these networks. So we can actually know what are the predictions given different changes to the input stimulus and different parameters of the model. They may not be interpretable, although interpretation has no mathematical definition. So they're not interpretable to you, but to me, they're interpretable because they follow the language of science, which is mathematics. So they are totally interpretable to me. But the points that I want to really focus on is that they're falsifiable. These specific models right now, and even improvements on these models, they're all falsifiable and they're usable. And the reason why I want to focus a little bit also on the usable part is that if things are not usable, then I don't have any motivation to falsify them, because then whatever. So I'm going to give you an example of why they are falsifiable and how the falsifiability helps. So when I started working on these models in 2015, feed-forward convolutional neural networks were the models of the ventral system that were most prominent. They were predicting a lot of data, unprecedented amount of variance in the data. So one great thing they could do is they're falsifiable, so they make concrete predictions. You can predict behavior of monkeys and humans, and then you can use those behavioral measurements to then further falsify those models. You can predict neural measurements on these areas. So you can stick an electrode, you can record, you can perturb these areas, and you can also use that data to falsify these models. So at the end of the day, it provides us to keep moving forward and improving these models. And I'm going to give you a concrete example very quickly. Is that so I did some of these experiments. We compared models and humans, and we found that they're not lying in this unity line where whatever the model is saying the humans are doing. So we used some of these images where the models were not really sort of doing the same thing as the humans. And then we asked, like, can we get some insight from the brain to tell what might be the difference in the models and the neurons and the brain. So then we did some measurement, we did some perturbation studies, and what we did at the end of all of this is we kept updating this models class, and now we are going to have models that are not similar to the same CNN or the ANN that we started with, but using the data, we have improved these models further and further. And you can start building them more and more sort of closer to the brain. You can say like, okay, you provided me this model, but I don't really know what happens if I do something to layer 3 of V4 cortex or something. If I only take out the inhibitory neurons of V2, for example, what happens? I don't have that understanding. Well, the first thing I would say is, okay, come up with a behavior where that is relevant. And then we can start seeing how we can make some changes in the model and whether those models then predict the new data that we are going to collect in the lab. So that is kind of my approach, at least the one that I will propose here. I think this is not that different from some of the stuff that Jack was also saying in his talk. The last point that I want to make is that, okay, essentially all models are wrong, but some are useful. So are these models, even the feed-forward neural networks that we started with, that we have now falsified multiple times, are those models even useful compared to maybe some of the semantic models or the structural models? So at some point we knew that V4 neurons respond to these complex curvatures, but now we have these neural network models, the CNN models. So we asked, can we use these models to basically answer the same question of like, what kind of images drive these neurons at higher levels. So we had this technique, and we started finding that there are different kinds of images that don't look exactly like these complex curvatures, but had some other kind of shapes and structures to them. Those came out of the models, and they were driving these neurons a little bit better. And the problem now is that it feels like the field is kind of saying that, oh, these are the understanding, these are the endpoints of understanding. To me, it feels like, okay, I was smoking cigarettes and I took that off, I started vaping, and now I'm addicted to vapes. So what I'm trying to say here is that at least that was not our point of view. This is not the understanding that we were looking for. The understanding that we were trying to highlight is this model itself, because this model is the ones that have predicted these images. And maybe with a better model, we will predict images that even further are able to predict exactly what the neurons would be doing. So it's not about the images, it's about the model and the predictions. The images were just a PR strategy to most effect, I think. And of course, this is not usable in the sense of like neurological disorders, but you might think if these images could elicit different moods in humans, for example, then you can think of that, okay, now these actually synthesizing these images might be useful. And the better model you have, the more accurate those predictions of the endpoints are from those models, the better the use of it. So I want to end with 4 points about this particular proposal. So first is that I acknowledge that this is the understanding, the CNNs itself of the understanding, because explanation in itself, I don't think this low-level explanation, they're just the sort of this is like a stepping point to get to the model that looks like the brain. So, okay, these are incomplete, they're wrong, but they're still useful in some sense. They're falsifiable, and that is the key point. So you can make concrete predictions that you can test in the brain, in behavior, so they are falsifiable. We are not, so I think the easiest way to get around feeding each other in some ways is to define an unfalsifiable field. So now there's no point in like debating or anything anymore. So I think we need to stay falsifiable. They're useful. As I said, V4 prediction might not be that useful, but maybe PFC prediction or amygdala prediction might be more useful in terms of neurological disorders. But the more important point is that because we have something to work with and falsify, we can improve them, because as I showed that we did studies where we clearly showed that recurrent processings are missing in these networks. Let's try and figure out how to best incorporate those things, and then maybe we'll make a more predictive network so we can improve them. And so with that, I want to end my talk and thank my great lab for supporting me for all these years, and I look forward to your comments and questions. Thank you.
That was great, Ko. So I'm writing with you, like Jack said. I think a lot of us are very excited by CNNs, and they are very, very helpful in what we do. I think you lost me in your last slide when you point out that the image synthesis that was permitted by your model was actually not the explanation, because image synthesis, these visualizations like Deep Dream, were made to explain neural networks. So you have with a neural network, the architecture, you have the circuits, you have basically the combustion engine in many ways, because you have like the specific filters, all the operations, you can put them mathematically in equations. So that's the mechanism, but the actual information and how that information gets transformed from layer to layer, that's what you learn when you do that kind of visualization. So
yeah, but when you do the visualization, there are many visualizations. So you have to pick some visualization and make some kind of wordage around those visualizations to then talk to each other. And I think that's fine if that is what you mean by explanation, and it's totally okay to aim for those after the fact these models exist and all that. So I'm totally okay with that. But I think that to have that before the best predictive models are already out there might be kind of a bottleneck to progress. And I also don't know, as I made this point earlier, I think what those explanations are and how satisfactory those are will depend on the generation, because like as I said in 300 BC, these explanations of like orientation preference of V1 made no sense. Now with more and more understanding or more and more of these models being available, some of even the terminology like convolution itself seems like an okay explanation to me to some sense right now after like 5-6 years of convolutional networks. And I think the terms and the things that we feel comfortable as explanation is just a shifting goal. And I think to bet our like money on that as the endpoint, I think will be problematic for the field. I think the endpoints are the neural responses to images that most likely are not going to change that much. They're going to be still the same kind of targets for, and as I think Carl was also mentioning, the causal studies. But to me, like the causal studies, the correlative studies, they all, at the end of the day, they will rely on some kind of prediction that needs to be tested. And the models need to predict those causal structures. The models need to predict the behavior, the neural firing rates, the transformation from one area to the other. So all of these independent problems, I think, can be phrased as prediction problems. It's just we need to hit them one by one and not, I mean, and that's where I think some of this intuitive understanding of the networks are actually important, because they might tell you where the networks are sort of like, kind of like at fault and how to make the next update. But to have that as the last word, to me, it seems problematic. But like, I would totally see if someone else wants that as their final goal, fine with me. I mean, my final goal would be to cure Alzheimer's or something.
I'm gonna, just for the fun of it, I'm gonna push back against the CNN thing from a different perspective, which is one of my favorite things to think about: image statistics. You know, a lot of people are amazed that CNNs offer features that are useful for brain modeling. And to me, that's the most obvious thing in the world. After all, you trained the CNN to learn image statistics. The brain evolved to learn image statistics. They're both constrained by image statistics, the physical structure of the world. I am not even slightly surprised that the stuff that the CNN learns ends up being useful for modeling the brain. But there's another tack on that, which is if the ANN is learned image statistics, the reason we're using ANNs as sources of features are because we don't understand image statistics. And actually, if we did understand image statistics, we wouldn't need ANNs, because we would just be able to generate the statistical dependencies that are most informative directly from math. So ANNs are kind of a cheat that gets around the problem that humans are dumb and our computers aren't that big. And so, you know, that's fine. It's a good cheat. It works really well. But again, in some sense, I think it's unsatisfying.
How is it a cheat? I mean, you know, how much longer do we need as a field to come up with the right image statistics? I mean, what these things do is tell us where we should start looking. And then it's not just the image statistics of the world, because the animals, you know, these are brains in animals. And the statistics of their natural world are going to depend on their ecology, on their behavior. So, you know, just having an understanding.
Well, that's where the ANNs fail the most, right?
Well,
ANNs don't have any of the I mean, even ANNs that have attention, the way attention is implemented in ANN is completely different than the way attention is implemented in an animal. Yeah. The only thing that ANNs share with animals is like when they learn, the representations change, and when animals attend and learn, their representations change. So they share that. But a lot of the task-based components of ANNs, we don't. It may be that they're useful. I have actually long argued that if we're trying to model brain responses to complicated tasks, like imagine somebody playing a video game or an animal playing a video game, that those tasks are so complicated that there's absolutely no way. We don't know image statistics. We don't know task statistics either. Your only hope is going to be to train an ANN to do that same task and then use that as a source of features. But that's the same kind of cheat. It's basically the ANN is being a substitute for the fact that we don't understand the structure of the world or the structure of these tasks.
I don't think the statistics themselves are sufficient. Like, for instance, you can have very different ANNs, let's say a convolution network versus a transformer-based vision network. And the convolution network seem to be doing okay at predicting responses, whereas the latest transformers, even though they perform very well on ImageNet, they do not predict neural responses well at all. So I think it very much depends on the details of how exactly you learn the representations in order to make sense of the image statistics.
Sorry, Martin, some of that got garbled. I wasn't really sure about the beginning of that argument, but.
My main point was, it depends on how you exactly learn the image statistics. So you can conceive of a convolution network that learns statistics based on ImageNet and a transformer-based network that learns on ImageNet. And both of them will perform very well on the task itself, but in terms of their neural productivity, they differ quite strongly. Like the transformers are much worse.
That's because they've learned different image statistics because the task sucks, right? So, I mean, you know, for example, it's real. There are not many open source, you know, non-corporate neural networks that deal with movies at all. Yeah, right. That's just beginning. And those kind of things are just missing. So, okay, so now you've got a CNN that's learned some image statistics, but not all the image statistics, you know, or they may be biased because of the optimization function that you were implementing when the network was trained. I think my point still stands that basically these networks are, when we're using them for neuroscience, they're a substitute. When we're using them as a source of features for neuroscience, it's a substitute for or a compensation for our lack of knowledge about the stimuli and tasks themselves.
I kind of did not understand the difference between understanding image statistics and maybe CNNs or some models, because those mathematical formulation of the understanding of image statistics, that could be like a kind of a CNN or like any NN or like ANN. It's just how we use those terms, I think, at the end, like, because they're just, if it's say some operation on the images to get to some other numbers, they're just, it's just, if I don't show an image of
just imagine quantum mechanics was implemented in a CNN instead of just a bunch of equations. How much better off would we be?
Yeah, I don't know.
I don't think we.
When I hear quantum, my mind stops to work. So
that's not a valid comparison, Jack. You know, CNNs are inspired. The original CNNs, neocognitron, were inspired by knowledge about what the brain does. Convolutions are, you know, not unlike the filter of neurons. They're organized in layers hierarchically. They decompose the worlds the same way. It's not the same thing. These are, in a way, more informative about what the brain does.
Even in physics, like you can make equations of how an atom works, but when you try to predict the weather, you use heuristic models that are maybe some black box in the language again, but they're much more predictive of than an equation.
I completely agree, and that's because humans are really bad at nonlinear dynamical systems. In fact, this is an example I oftentimes give in my classes. If we could record from every single neuron in the brain, we would transform neuroscience from being a measurement limited science to a model limited science, because no one would have any idea what to do with those data. And we probably fit a network.
In fact, I want to say that, well, as Ko already said, nobody knows what the data we already have, how to interpret that. I mean, CNNs do the best of the models we have, but that's still not very good. It's less than half of the variance. And maybe someone in this workshop will say that they also don't generalize very well if you vastly change the image statistics. But I also want to add, maybe a little related to your point about prediction and understanding. You said we don't yet have a good model of image statistics, but will we ever have that? Or are CNNs necessary in order to do that? Like, we understand quantum mechanics, we understand like dynamics, but we cannot predict protein structure because they're just too large. If you try to run the physical equations, you can't do that for very big proteins. And it turns out, you know, statistic-driven approaches like AlphaFold, they are able to fold proteins, probably for the wrong reasons. But so like, if we have a two-dimensional prediction versus explanation, how do we even pick what's our preferred outlet?
I think understanding just acknowledging the limitations of the different methods and using each for its value is probably the way to go. I mean, I don't think we need to pick between them, right? I mean, I think just not declaring that your model is the best and you are the winner is the way forward. I mean, you can't have one model doing everything.
I totally agree. And I think I see the falsifiability. That's why I kept pushing the word falsifiability, because I think the fact that some of these CNNs are, I think CNNs are not special, they're just a family from like the artificial neural network. The fact that they're falsifiable, that you can tell that they're wrong, and in many ways, they are adversarial examples, blah, 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 many things. That to me is like a very, that to me is the biggest value that they offer. Because if they're not falsifiable, then there's no progress in my mind. You cannot really make any progress otherwise. So I totally think that like they're super, you can say like only maybe 2% of the ventral stream has been addressed. Maybe we are claiming 50%, but those are biased, recordings and like specific ways of looking at the system. But to me, even if it is 2% and falsifiable, and there is no other model that comes close, they are the best models, and we have to improve them. And maybe they won't stay convolutional. Maybe there will be something else, but that framework will still stay the same. There's a model that predicts. You go and test, and you tell me how to change this model to predict better. If it's not predicting to ceiling, it's kind of what I.
Anita, I'm curious whether you think that these different approaches have to be integrated in some way, or whether they could all just be doing their own thing independently of one another and used for their own different purposes. And if you do think that they should be integrated, going back to some of the things that Jack was saying earlier, what do you think that integration would look like, or what?
I think Jack might have said this already, but I want to reiterate that I think with every data set, we should try to fit every model. And we should try a variety of models at different levels. I think of all these models as attacking the problems at different levels. And so try and fit the data set with a variety of models, and then try to understand why some models fail and why some models succeed, and try to look for correspondences between models and use that to improve the models. I don't think we're at a point where we can drop any model just because it doesn't predict the responses. I like the falsifiability idea, but I don't think you need to pick the winner and then just try to improve it, because maybe one model will fail with a certain data set. But I think we're at a point where we just need to keep a lot of models alive, try to fit all of them with a variety of data, try to test them, try to do predictions, and think about it from a variety of questions, and move forward and do lots and lots of experiments.
Totally agree.
But can I mention an example of the sort of synthesis that I think Carl is talking about that originates with Anitha and Wyeth's work, and that is to combine structural models with CNNs by testing CNNs and the CNN artificial neurons in the same way you test neurons in the brain, and then apply structural models to them. And Anitha and Wyeth were the first to do that with two-dimensional information, structural information in V4. And the work in our lab by Ram Srinath, who's been on the comments here, showed how that even works for 3D, which was a great surprise for me. I didn't think that you would have really explicit 3D structural information inside AlexNet, but you do. So I think you can have direct synthesis where two things that appear to compete actually say the same thing and are confirmatory rather than competitive.
Yeah, looking forward to that talk. I think, Thomas, we're going to do a little coffee break.
Yeah, there was some controversial stimuli sessions as well. I think that was also probably very relevant to the last points that were made. I think that seems like a very nice way to pit models against each other to see how to compare them and where their predictions mostly lie. And Nico has done a lot of work on that. I think that's very relevant to this discussion.
Great. Let's put a pin in that and come back in 5 minutes.
And is it me next, or
I believe so.
Thomas?
Yes, I think you are next.
Okay, thank you.
I think we can resume.
It would be hard for me to say they're not mechanistic.
It would be hard for you?
I mean, if you believe in the simple complex transformation in V1 as a implementable version of pooling, if that's a mechanism and that's part of the CNN. Sorry, you're an echo.
And just to add to that question, I think like as function approximators, like different layers, like kind of approximate different kinds of functions, and that's pretty nice. And so I would say like the hierarchy in the CNNs and the hierarchies in the ventral string kind of aligned, and that part I would say it's mechanistic. but like for how it implements in the CNs, I won't say that's mechanistic.
So if you had a model that predicted just as well, but a CNN predicted V1 through V4 just as well, but didn't align layers to our understanding of the position of brain areas in the hierarchy, would it be just as good a model? Not as good?
I think there should be scoring of the models should be based on different benchmarks, and what you're saying is that it will fail miserably on the architectural benchmarks. So depending on how you score the model, they will really predict V1 and V2, but maybe V2 comes before V1 in those models, then they will fail on the architectural benchmark. So I think at the end, depending on how you score these models, it should have be. That's why I think it's an integrative benchmark approach. It's like you have to think through like how exactly.
I'll say it would make me look twice at the architecture, right? Like we still don't know how to map layers to areas. What if, for example, different, cortical bands actually correspond to different areas, and it would make me look again and see, did I miss anything?
But even in the brain. Too.
Yeah, in the brain.
Yeah, exactly.
Our assumptions about the ventral hierarchy.
Yeah, I agree.
Cool. Well, I think we can get started again. Anitha's here. So Anitha, if you want to share your screen, we can resume.
Okay, so are you able to see my screen? Is it good? Okay, so as I've said, I'd like to use my time to advocate for fitting the same data set with models at different levels, and also to assess the correspondence between different types of ventral stream models. So let's say we're trying to find the function that maps the stimulus space onto the response space. And we've already said many times now that models can be of different levels. For example, you could have a CNN, a deep convolutional neural net model, or you could have a variety of other models. For example, you could have a model that's based on the structure or the geometry of the visual stimulus. Now, if you're going to compare these models on the basis of their predictive power, how well do these neurons predict responses to novel stimuli, you could imagine that these models might be equivalent. But when you start to ask other questions, for example, how do the neuronal responses support a certain kind of perception? For example, the differences between these models might lead you astray in terms of the answers you come up with. And so I want to try and illustrate this with an example, with a concrete example, because all of these are lots of words I've said. So maybe an example will help highlight what I'm trying to say. Okay, so I'm going to use the example of texture selectivity in V4. So Komatsu and Okazawa and colleagues did some beautiful experiments where they studied the responses of V4 neurons to a lot of different kinds of naturalistic textures. They used texture synthesis algorithms and adaptive stimulus selection procedures to study responses to lots of stimuli. There were lots of, for each neuron, they identified preferred textures, non-preferred textures, and then they took all of that data, and for each neuron fit a model. And the way they fit the model is by using higher order image statistics. So basically, they described every texture in terms of the Protea-Simoncelli statistics. And intuitively, this is a description of each texture, not just in terms of its orientation and spatial frequency content, but also higher order statistics, for example, orientation cross position, orientation cross scale, etc. Okay, and then the responses of each neuron were fit as a weighted sum of all these texture statistics. they got reasonable fits, roughly explained about 25% of the response variance across all of the V4 neurons. And when they were faced with the question of how might these neurons contribute to categorization of texture, for example, how might you differentiate between a texture that is coarse versus fine, the authors did some modeling and hypothesized that this might be based on a population-based representation. So for example, each neuron is sensitive to a bunch of higher order statistics, and different neurons are sensitive to different subsets of these higher order statistics, and together they might be able to contribute to your ability to discriminate between a texture being coarse or fine. Okay, so implicit here is the idea that a single neuron is not sensitive to this coarse fine dimension, but it's really at the subpopulation level. So we too were interested in this question of how do neurons contribute to your ability to perceive textures. And so we also studied responses to a variety of natural textures. And then in fitting the data, rather than just going with higher order statistics, we represented the texture in terms of structural texture attributes. So the coarseness of the texture, the contrast, regularity, and directionality. And the reason we chose these attributes was because we found in the human psychophysical literature that these were the dimensions that were critical for texture similarity judgments in human subjects. And it's also, these dimensions also fall out from computer vision exercises in which they try to decompose homogeneous random fields of texture. And so so we devised metrics so that we could represent each one of these textures in terms of these dimensions, and then fit the responses of V4 neurons on the basis of these 4 dimensions of texture. And we got very similar fits to theirs. I mean, we were, again, the median explained variance was about 25% across these V4 neurons. And so in terms of, I mean, we haven't done a head-to-head comparison with their model, but one could imagine the predictive power for novel stimuli, these models might be very similar. But there is one fundamental way in which our model differs from theirs, and it is in the responses of single neurons being sensitive to these various structural, perceptual texture dimensions. So here is an example of a V4 neuron that responds more strongly to coarse textures as compared to fine textures, and you see a strong correlation with the coarseness metric. Here's another example of a neuron that responds stronger to non-directional textures compared to directional textures. Again, there's a reasonable correlation. So the conclusion from our study would be that there are individual neurons in area V4 that are sensitive to these structural, perceptual metrics that would probably be related. So we're now working on trying to relate these different texture metrics to the higher order statistics. So for some of them, for example, coarseness or contrast, there is a very clear relationship with the power spectrum. And so we can relate the higher order statistics to these. Directionality and regularity, it's a little bit more complicated. So we're now trying to see how our model translates into their model. So just to summarize very quickly, we have 2 models here that explain responses to texture equally well. If you were predicting novel stimuli, perhaps they would be similar. But if you want to sort of ask how these, higher order, how you might build up these models, then you might want to look at the correspondence between higher order statistics and these structural representations. Okay, with that, I'll stop and take any questions.
Anitha.
Yeah.
Do you suspect or speculate that this kind of preference for oriented textures versus non-oriented, for multi-orientation textures versus single, might actually reflect that some neurons are concerned with encoding shape, which tends to have multiple orientations in it?
Yeah, that's a great point. And so that experiment that we did actually was, in that study, we not only studied the responses to textures, but also shapes. And so it's, so we can actually compare preferences for texture versus preferences for shape. And neurons that are more sensitive to texture tend to be less sensitive to shape and vice versa. And so I'd have to look at your specific point of non-directional textures being sensitive to shape. That's something that I haven't looked at, but that's a great point. That's something we can look at.
Very interesting results, Anitha. I confess, just in the context of the conference, of the workshop, as I saw those shapes of textures, they reminded me a lot of Koh's paper and the kind of images that they could synthesize using that approach. Is that a superficial similarity that I just caught, or do you think there's a link?
I think there are lots of neurons in V4 that are sensitive to texture. And as I said, I mean, there seems to be, so a lot of the neurons that are sensitive to shape are also sensitive to texture. So there is joint tuning, joint separable tuning for shape and texture in these neurons. But driving neurons with textures are a lot easier than driving neurons with shape, because when you're a neuron that's sensitive to a shape, you have to hit the receptive field quite right. Whereas with these texture sensitive neurons, you could have, large fields of homogeneous texture, and surround suppression might suppress the responses. So when you stick an array and record responses of neurons, my suspicion is you are likely to find neurons that are more sensitive to texture as compared to shape.
Can I expand on that, Anitha?
Go ahead. Yep.
So the same thing strikes me, Carlos, and has struck me, not only in Koh's paper, but in Marge's paper looking at IT with related techniques, that so often the superstimuli are stimuli that look texture-like in the sense that they have these repeated motifs. And at least the suggestion that I suggested in the current biology dispatch that Koh knows about is that if you've got a neuron that is shape sensitive, and then you present a stimulus that has 5 of those shapes in it, you may get stronger responses, because neurons need to be position invariant. They've got to have mechanisms for multiple positions. And if you stimulate multiple positions, you may be driving them at a rate that, and what do you think about that, Marge? I feel like you got many results that looked like fields of eyes.
Yeah, sometimes, but you also get normalization. So you can have surround suppression by similar stuff, even within the same receptive field.
I can ask another question. So Anitha, I like the part of your talk when you're describing the structural texture attributes, the ones that you chose. You had a strong rationale for why you chose those. And one of the things that I struggle to understand in ventral stream studies is how one chooses, or the space, how one constrains the space of rationales for choosing the right attributes to use in one's studies. And I'm just curious, clearly you had a strong one here, but in general, how do you approach that issue?
Yeah, that's something you struggle with, right? You have an experiment you're doing and you have a certain number of stimuli that you can present. So you have to choose your stimuli. Fitting your responses, you can try all different kinds of models, right? So it's the choice of the stimuli that becomes important when you're trying to explore the space. And so a lot of the way I try to do it is try to use a lot of motivation from psychophysical experiments where they have explored a lot of different dimensions, computer vision studies, right? And so a lot of times we would create stimulus sets and discard them and start afresh. And so it's really the experimental time with any given neuron that constrains the kinds of stimuli that you use or the space you explore. Yeah.
Can I suggest another synthesis? Because throughout the year, I'm going to be pushing the idea of synthesizing things of Anitha's results and Ko's results and Marge's results. And that is, in addition to the repetition of motifs, something that jumps out to me about textures, the textures that Anitha is using, especially because they're natural, but even the textures that evolved in the other V4 experiment and the IT experiment is that they have a three-dimensional appearance to them. They do not look like two-dimensional patterns. They look like three-dimensional patterns in relief due to shading. And again, referring to work by Ram, who is at this meeting, his experiments showed that over half the neurons in V4 are much more responsive to 3D shape, and specifically 3D shape from shading than to 2D shape. So across the texture experiments of Anitha, across the stimulus generation experiments from the Livingstone and DiCarlo labs, and even across experiments that Jack used to do with spatial frequencies, and many people used to do with spatial frequencies. It's well known that you can drive V4 neurons well with sinusoidal gratings that also have this light to dark gradient that's characteristic of 3D shape, and sinusoidal gradients actually look like 3D corrugations. I think these things all agree.
So Ed, I think they look 3D because of the boundary blur. So when you mask them with a solid boundary, a sharp boundary, they don't look as 3D as when you blur the boundary.
Yeah, I don't mean that the whole stimulus looks 3D. I'm saying that things inside the stimulus look 3D.
I see. And so do you see, that's very interesting. So do you see any, what is the latency of responses for these 3D stimuli? Is there any delay at all? Do you see these?
So Ram could answer this better, but I'm pretty sure he looked at differences in latency between 2D neuron responses to 2D stimuli, 3D stimuli to 3D, and did not find anything.
Oh, that's it. Very interesting. Yeah.
Yeah. But again, I think there's potential for unification across dimensionalities.
Yeah, also like to chime in a little bit, like in our setups for using generative network and search, we already sometimes find those kind of like very seemingly shape from shading stimuli, like have a gradient of like color or things, and you can see the 3D shapes. If you want to see, I can share screen just a little bit.
Yeah.
So it's so this is like some of the things we evolved from like V4 arrays, and for like this stimuli, this one,
Yeah.
and some, yeah, you can just kind of see the shapes just from it.
Yeah, I agree.
And like this one, I haven't applied the importance mask on it, but basically it's the thing you see. It's the thing that's important. So I can imagine that is like kind of related to what you are saying about like 3D neurons in the V4. Another little point I want to jump in is, so you said the DiCarlo labs generate lots of texture things in their stimuli, and our approach kind of generates more of the like less, in some cases, less high frequency things. I think there are some priors or biases built in the methods. So in the DiCarlo labs methods, they use like low-level parameterizations, and we use like high-level parameterizations. So the GANs usually generates like less high frequency stuff usually, and the image, so it's give a stronger regularizations on the image you can generalize, and DiCarlo lab give us weaker prior on that. So
there's a little like, I think there's a separation between the image generation part and the test and the predictivity of the model and the goodness of the model part, right? So you can have multiple ways of generating images, and if we discuss about what those images are, that seems like a very different conversation. Like once you generate those images, whichever way you play them back, and then it either matches the prediction of a model, which I was producing as like the understanding of the system, the current understanding of the system, either matches that or it does not. And I think I would like to focus the discussion there, because we can look at these images all day, all year, all months long, and then we'll not reach anywhere, because there are deeper questions of like the neuron that you find in one monkey with some preference, does the same neuron appear in a second monkey? What is the shared variances across monkeys? What are we actually trying to model? Are we trying to model individual monkey neurons, or are we trying to model like the shared variance across humans and across monkeys? I think these questions become relevant in these discussions. So I don't know how much of the discussion of what those exact stimuli are is helping us to understand anything, unless they are basically framed as a model update.
But the
this is where I would
like
to.
I think Gabriel you're setting up Gabriel very nicely, Ko.
You never know beforehand, right? This is the classic problem. You see this reflected a lot in science, where it's unclear. You collect a bunch of data, and it's unclear whether you want to model at the individual level or the group level. That's true for psychology experiments. It's true for neurons in neurophysiology, right? So the only safe thing to do is model both, because it's hard to tell which one of those is going to be important and when they're going to be important.
And that sets up the final panel very well, the experiments that we're going to propose.
To expand on Binxu's point a little bit, maybe you said this, but I think even the training stimuli for the models that are then used as sources can have a big influence on what they're going to produce.
We wanted to also make sure that if there's any comments in the chat that are worth bringing up or highlighting, that would be a good thing, certainly during this lulls in conversation. So did anybody that posts something in the chat want to bring it up again? A science button.
There seems to have been some discussion of a magical science button.
I retract my statement.
Okay, well, that's about that's 20 minutes. So 20 minutes. Moving along, I think we'll have Gabriel is next. You want to share your screen?
All right. Can people see my screen? Yes?
Yes.
Good. All right. Excellent. I'm gonna show you where science button is. Okay, so I'm gonna be very brief here. I want to give you my views and a quick summary. Maybe I'll iterate some of the excellent points made by all of you earlier. So I refer to word models, tuning curves, and computational models. This is a separation that maps up somehow Carlos' initial description, but basically many of us are probably in between multiple. So I want to emphasize again what Ko said earlier. Whatever models we end up coming up with, they have to be falsifiable. If they're not falsifiable, it's not science. I think there are a lot of reasons why we want image computable models, and I want to emphasize what Anitha said earlier. So there are many models that can be based on trying up with tuning curves that can be very well incorporated into a quantitative image computable models. So these types of tuning curves are not really dissociated from computational models. And along those lines, I want to say that I generally talk about computational models much more than CNNs. When we talk about CNNs, several aspects that I think many of us are quite unsure about. For example, it's clear that our computational need to be deep sense of having multiple layers.
Gabriel, I'm very sorry, but you seem to be echoing for everyone.
Can you try turning off your other instance of there?
How about now? Is this better? Yes. Okay. Yeah. I turned off the speaker, so now I cannot hear you. I'll have a no.
A little bit echo. It's a little bit of like static, and it just cuts off.
There's still a lot of echo. How about now? Better, worse, same. I see a couple of thumbs up.
Same.
Some thumbs up. Yes. Okay. All right. I wanted to say that computer models to me is a much more generic term than CNNs. When we talk about CNNs, there are tons of assumptions about how many layers we need, whether we need convolution or not. I think all of these are up for debate. But I do want to emphasize the fact that we need quantitative, image computable, falsifiable models. And personally, and I think here there will be major disagreement. I'd like to stay from the discussions about elegance and subjective nature of models. I think that we can debate about elegance, finance for. Personally, I find a model that's well defined and I find to be extremely elegant. And I'll be very happy to see quantitative computational models. I think we understand CNNs perfectly well. They're perfectly interpretable. We know exactly what each round is doing. So I want to stay away from all these discussions about whether they're ugly or not. Because our current computational models are far falsifiable, I'd like to do just that. I'd like to falsify them. And the main point I will make is that I think computational models are ultimately the way to move forward. But current models are false, and we need better ones. And I think that there are ample opportunities, as Ed and many others have pointed out, for synthesis, for unification, and for jointly build better models. So you're probably already quite familiar with some of the aspects. So I'm going to go very, very quickly. Many of the current computational models that many of us are excited about in terms of how well they can predict firing rates suffer from major failure modes. One of them is adversarial images, illustrated here, where you can take any image, like a school bus, a very amount of noise and convert it into another image, as stated by the classifier, by a typical CNN model. In some cases, the noise that you're adding is imperceptible. In fact, you cannot even render it on a computer screen. Here's another example. This is a very nice paper by Gabriel and colleague, where they show basically that current CNN models are extremely biased towards textures, much more than Jeeps. and that doesn't match our behavior and our perception. So these are, I think, are two strong arguments against our current computational model. But given that one of the points that we want to make is to try to understand the inner workings, the neurons along the ventral visual cortex, I want to give an example of how we can falsify the best computational model we have today. And so for that purpose, I want to introduce work that many of you have already mentioned. This is work done by Ponce and Will Xiao, who's here, and we'll talk more later. Peter Schad and also Mark Livingstone developed this algorithm that they called XDream, which basically has three components. It's a generative network that creates images. Another one is recording from a neuron as a fitness function. And another one is just a genetic algorithm that will recombine these codes to be able to to generate neurons. So this is an unbiased automatic discovery of neuronal references. We can come up with images starting from noise, essentially, driving neurons to very high firing. And I think it's very important to know that one of the main inspirations for this is the work that Ed Connor did many years ago in a somewhat space, starting with curvatures and tuning curves, but also using genetic items to try to discover what would it like. So this is essentially an updated version of the very nice work that Ed did, but incorporate some of these convolutional network. So basically, you start with noise and create images that drive neurons to very high firing rates. So here's one example, and this is a work that was done by Will Xiao here, and he may say more about this later, where he was recording the activity of a neuron in response to many reference images, many natural images, and he used the convolutional neural network to predict the firing rate of that neuron to other images, other natural images within the set. You see here is similar to the work that Dan Yamens and Jim DiCarlo and many others have done. You can predict the responses of these neurons, of this particular neuron, pretty well to these reference images. So what you're seeing here, each dot corresponds to a different image. You have the predict firing rates on the x-axis, the observed firing rates on the y-axis. So this is quite impressive, and it works pretty well. But then you take the same neuron, you run the XDream algorithm to generate novel images that are quite different from the ones that model was fitted on, or perhaps over-fitted on, and here are the responses and the predictions from the same model that we were so happy about one slide ago to these XDream images. So I think it's pretty clear that this model is not a good descriptor of the responses of these models. And saying you can actually do what Cole was referring to earlier, take a computational model to try to generate images and then make predictions for the rate of those images. And that's even worse, basically. So that just doesn't work. I mean, the predictions that the model has for this neuron are just very poor. So again, this is just to iterate some of the points made by Ko and the others. Here is a very clear case where we can falsify our computational models. So this is not to say that that the computational is not the way to go. I think it's the way to go. I think we need better models. There are plenty of room for improvement. This is just one of many examples of how we can use quantitative metrics that don't depend on any subjective discussions about elegance or any other relations, where we can have very concrete quantitative metric where we know that models, as exciting, as elegant they might be based on this curve here, they still fall quite short of a comprehensive understanding of neurons in ventral visual cortex. This particular neuron here is in posterior inferior cortex, but similar conclusions can be drawn in other areas. So that's all I wanted to say, and I think I'd be happy to do any questions, or otherwise we can go on to next second.
It seems like you're arguing that you should do prediction first and get good predictions, but which I obviously agree with. But then at the end, you're still going to have an elegance issue, because if you have more than one model, then you have to decide which model you prefer. If they have the same predictions, then you can't use the predictions to decide between the models.
I think this is slightly different.
So I argue that then we come up with better tests and new models. Not I think elegance should be reserved for fun, not for science.
Gabriel, what do you think, since you've posed this problem of needing better models, what do you think are the most promising, even radical directions for models that are better in a qualitative leap sense, not just incrementally better?
I think there's plenty of things where you know better than me about all the biology that's missing in these models. Many of these are don't have recurrent connections. We've done models that incorporate recurrent connections. Co and others have done that as well. Dynamics are critical. Jack mentioned the importance of studying movies and dynamics makes that most models lack completely. These models are quite primitive in terms of the complexity. If you just any new connectomics data on the complexity of the circuitry, I think it's very clear that there's tons of internal recurrent connections, lots of horizontal connections. I can keep talking forever about all the things that are missing in these models. I cannot quite tell you which ones are the most critical ones. I think that we need to incorporate every single one of the 3 or 4 tens of different types of interneurons that exist. I'm not sure that that's critical, but I think it's very clear that these are as excited as I am about these models. That it's very clear that they are very primitive and there's biology that we need to incorporate into models.
Yes, I agree with all that, and then I would also refer back to something Jack adverted to. I think that is that the training paradigm, the tasks that models are trained on have to progress. So I've always thought, and I think Jack said something like this, that, you know, if you really wanted a good model, good artificial network model of the human visual system, then stick the thing on a robotic platform with manipulators and let it wander around the world for 12 years. And then you would have something that was a lot closer to the human visual system.
Yeah, I don't disagree with that. I think that 12 years is a little bit beyond the time scale of my grad student, but certainly the notion that we need to study better paradigms, the notion that natural statistics are critical, notion that that there may be a lot of unsupervised learning that happens as a baby explores the world. I think that's all very, very exciting. There are initial attempts in that direction, and I think that they're going to be very, very fruitful. Again, at the end of the day, I think we need to do models that are falsifiable, image computable, quantitative, and compare them in quantitative ways. But I do agree with that. Training models in a supervised way with 100 different varieties of breeds of dogs, as we would ImageNet, is not necessarily the way to go, and there are much better ways of doing that. I agree.
Gabriel, do these results not highlight the issue that Jack brought up at the beginning about the out-of-domain failures? Like, if these models, so the failure here with the CNN is not actually good at generalizing to weird kind of generators that we have at their disposal. It's never seen it before. But if you train presumably a neural network with more images, would you not get better performance here? More images that are just photographic and generator based and anything.
Well, I haven't heard of a result where training
we'll say much more than I can about this. We tried a couple of different ways of training and incorporating novel images. I'm rather skeptical of this argument, because at the end of the day, you can always say, but we need to train with the green images and with the orange images. And if you always have to retrain your model with your test set, it becomes circular. And I want to have models that can really populate to new image data sets, right? So I'm a bit concerned about the argument being, we can rescue CNN models by training data and training on images that are similar to the test set. For sure, if you train with images that are almost identical to a test set, the performance will be much better. But I don't think that that's really what we really want to achieve in terms of a model that can generalize.
No, that's true. You have to, I mean, generalization is key. If you can't generalize, then you know that you overfit. So, there's overfitting to individual data points, but there's also overfitting to a subspace of the entire stimulus and task space that you want to explain. And because you can overfit to anything, right? So
I cannot agree more. And I suspect that a lot of what we're doing with current CNNs is overfitting to a subset. Not really overfitting in the sense of just taking the same pic, but you can change 5 pixels and that's legit cross-validation, but it's very trivial interpolation. So I completely agree. I think the question of generalization is critical. I think this is one of the many examples that show that current models fail to generalize in a major way.
So originally, I think part of this block is that I wanted to elaborate a little bit also on this extreme image synthesis approach. I'm sorry, I can't pronounce it. I'm from Mexico. I never quite learned that. But I do hear an echo. Gabriel, would you mind just muting yourself? Okay, does that sound better? Okay. No, I think do you guys hear anything? Okay.
Good now, yeah.
I am muted.
Okay, great. So the idea of the image synthesis seems a little bit more powerful to me. And I wanted to qualify this idea that when one generates this kind of image, it's not really meant to be an endpoint or the final explanation. They are supposed to be, let me just move this here. They're supposed to be tests. They're supposed to be kind of ways to determine and understand what the kind of information that is encoded in the visual system and in CNNs as a way to differentiate them. So this basic use of generators isn't something that we invented. It originally was developed for explaining CNN. So if CNNs are explanations, this is like the explanation for the explanation. And in a way, the way that we use it is a little bit a more literal version of what Hubel and Wiesel did, where we have an iterative process. They were listening to neurons emit firing rate, emit different spikes, and they were drawing by hand now, and to come up with different receptive field shapes. And basically, what we're doing here is just replacing the hand of Nobel laureate with a generative network. These internal representations are, which these are some examples that we capture from inferotemporal cortex. To me, they become more of a test of like when you have a couple of neural networks that do a very good job of predicting the responses, the firing rate responses of a neuron to a specific set. If you now understand the kind of representation that it encodes, and as Gabriel pointed out, some neural networks are very texture-based. So some of these model neurons might actually evolve things that look completely different. Some neural networks might evolve things that are a little more object-like, like this kind of representation. And in that case, I think that these images have told us a little bit about which explanation of the, which neural network actually did a little better job at approximating what the brain is actually doing. And what we really like about this approach is that it seems to work everywhere, right? It works in primary visual cortex, where you get little lines, in V4, where you're going to get interesting patterns like that combine contours and combine curvature. And in IT, you get object fragments that are reminiscent of many objects in the real world. And in fact, this even works in lateral ventral prefrontal cortex. This is work that Binxu and Olivia have been doing. So I think that this kind of approach does bring us closer to understanding vision under naturalistic conditions, which is something that Jack's been championing for a long time. It really inspires our research program, and I think it's a need that has been built in the field for a long time. Like Rustin Mopshin's classic paper, where they say the responses to natural images will always be the standard against which models are tested. There's other advantages, like, it minimizes any kind of constraints. We talk about overfitting models, but our explanations can also be overfitted to, the response of neurons to very limited image sets. This is something that actually gets us out of that and allows us to make predictions for any kind of image in the world, of predictions of how neurons respond to any image in the world. In the way that we've done it before is that, once we have the synthetic image, we can, provide us an input along with hundreds of thousands of images from any data set into any image computable model, like a convolutional neural network or some of the others that hopefully are in the pipeline. And that allows us to then use a number of different distance metrics to try and understand which features present or which visual attributes present in the synthetic image are present in the test data sets. For example, images in the real world. And it actually works really well. We've continued to use it in many ways. So this is something that tells us how to predict the responses of neurons in the natural world. It's not the final explanation, but it does give us a tool where we can take now images, for example, from generators, from photographs, any image that has been manipulated with a computer, classic visual stimuli, and we can actually see how the neuron responds to all of these different out-of-domain images by plotting them along things like perceptual distances. There's a number of different distances one can obtain, but they all kind of tell us the same thing. They seem to be telling us that neurons, individual neurons, are acting as filters that are responding over very large image transformations. And what really puzzles me, as somebody who really started thinking about neurons in the ventral stream as signaling values on unique axes or categorical spaces, to me, there's still a bit of a puzzle about why our method works at all, why generative networks work in this context. Because when we start with images that, they're random samples or black and white. There are a lot of things, they have a lot of information, but they're not faces, they're not categories, they don't represent unique values for any specific parametric axis, and yet neurons don't seem to care, where they're able to navigate the space of the generator just fine. So like if we thought of let's get a little romantic here and think that romanticize the idea of the generator as something even more powerful that really encodes the space of all 256 by 256 pixel images. So every image that has been used in ventral stream that was put on a computer screen exists in this space. And if neurons really are tuned to very special axes or to specific regions that can be described by things like categories, it is kind of puzzling to me then how the neuron is able to inform the algorithm to navigate this very large space without faces, without special axes, and to actually increase its firing rate to get closer to some of these images that I've showed you. And the only thing that I can think about is, again, going back to the very old idea of the neuron as a filter, that neurons really are tuned, they're informative over a much, much larger region of image space. And this is something that is that Binxu is pushing now in his latest manuscript that he's going to submit, where really one way to think about these neurons in ventral stream are a little more like hippocampal place cells, where it doesn't really matter. What matters is their location of their visual attribute tuning in image space. It doesn't really matter how you approach it. The axes don't matter so much. What matters is where that attribute center is. Again, this is an old idea. This is just the idea that neurons are filters. David Van Essen also pointed this out in 1992. And I think it's a point that is vividly made by convolutional neural networks, which learn without necessarily much, which learn a lot of the structural components in the world that we can name and that excite a lot of us without necessarily explicitly having anything built in them to do it. So what I wanted to add about the image synthetic approach is I think that we could stare at pictures all day and like Hubel and Wiesel did, and can try to synthesize a larger explanation, but we need them. We need to know what the visual attributes are. We need to know how they're learned. We need to know if different brains learn the same features, if they share the same ecology, if they work the same way. They should. And we would expect that CNNs, the ones that are behaving more, that are making the predictions for the brain, outside of something like, above and beyond what something like brain score would tell you, they should be learning the same features. But ultimately, the bigger problem is that if indeed it's all a trial and error process, it may be the case that some neurons are encoding features that have no easy way, no quick explanation. It's a little bit more like trying to explain the evolution of the whale species, right? I mean, there is a truth to that, but the explanation is a history, right? Maybe in this case, the experience of the animal is necessary to explain why a particular visual attribute has been learned by a given neuron. So that's it. That's what I wanted to say, piggybacking on what Gabriel pointed out. Am I overly confused here?
I think
we have a question from in the chat. That was kind of fast, and I want to make sure I understand. IT neurons might be place cells for image space. Maybe you could elaborate on that.
Yeah, so basically, if you consider the generator as representing the image statistics of the world as best as any neural network can do it, it's a very powerful space, 4,000 dimensional space. There are better ones, but let's say that that encodes image space. We're starting near the center of this latent space where there's nothing that makes sense. And yet, by using the evolutionary algorithms that Ed Connor has highlighted before, we can get the neuron to navigate this space and end up creating features that are often interpretable semantically. They're always interpretable parametrically by just describing them as a position in a neural network or as a set of activations in a different neural network. But sometimes they're not. Sometimes they're not descriptive semantically. And I think that actually it arouses responses from investigators. The idea that maybe they needs to be more on top of that filter than what it is. And that's the part where I sometimes don't know where to go.
I think this is a great point, and I think this is the last session, so I think it's a great point to end on. That is, what happens when visual dimensions are a dead end? And I think what you're saying, Carlos, with your comparison to hippocampus is something that I think very strongly about what happens as you pass from the end of the ventral stream into medial temporal lobe areas like perirhinal, entorhinal, and hippocampus. And that is that you actually move from visual space, from geometric space, to mnemonic space. And what you're seeing doesn't just represent, tuning manifolds on image or object geometry. You're seeing something that represents the learning of co-occurrences and co-meanings if you're trained to categorize things. So yeah, I think it's, and I think your experiments show this, right? So strong responses to images that really look like they don't have any common geometry, but I think potentially, I don't think we have to throw up our hands. I think we have to consider the possibility that at some point in any system, we've got to think about dimensionalizing mnemonic space, not just geometric space.
Would you think that semantic space is the place to look?
I wasn't thinking that, but I think it's a great place to look. It's a place that Jack has looked with success, by using systems for understanding the relationship between words in language. And yeah, so yes.
Yeah, but for vision, it seems, I don't know, at some point, the question is like, what a primate doesn't have language except for whoo, right? And a few other things. They don't say much. So, but they must have some internal representation of objects. So I assume, based on our similarity to them, because we're basically just big monkeys. So since we find it very easy and facile to assign semantic labels, and there's a lot of explicit semantic representation in the brain in this whole amodal system, I assume that vision, probably in primates, at some point is semantic in the sense that they, whatever their semantic representation is. But I personally, weirdly, I find that kind of an unsatisfying model. And I don't find it unsatisfying because it's semantic. I find it unsatisfying because really we can't, if you take any of these neural networks and try to just semantically label natural images, there'll be a few good examples and 80% of it will be Drek. And so you can't, there's no automated way to get semantic labels out of images yet. The algorithms just aren't good enough.
So
that's disappointing.
I'm afraid I'm in the uncomfortable position of having to stop this conversation so I can talk. But I want to make sure that we have time for everything else that's going to happen in this session, and if we don't stop, we're not going to have time for that. So I'm going to start sharing my screen, and are we good, Thomas? Yeah, all right. So I want to try to say, first of all, I want to thank Carlos for inviting me to be involved in this really fascinating discussion. I've spent the last couple of weeks reading your papers and trying to get my footing in this very complicated and fascinating area. I wish I could tell you that I was going to sort out all of your problems in my 10-minute philosophy presentation, but I think that that's probably not going to happen. And I'm going to limit myself to just trying to bring out a few of the things that have been under discussion here and to display some of the assumptions that seem to me to be underlying this discussion, in the hopes that that scaffolds clearer discussions going forward. So one thing that I just think is really fascinating in all of this is that it illustrates the kind of bidirectional influence of the tasks that we use to measure things in neuroscience and the models or putative explanations that we're considering. And I'm rather struck by the fact that different people have different task model pairs, and that the people in those different task model pairs have different values by which they're going to assess the outcomes of these scientific endeavors. And I want to bring out some of the differences in those values. And I worry sometimes that, if we just start insisting that prediction is everything, for example, then we're going to leave out those who think, well, having an intelligible model counts for something as well. And then we're getting into a discussion that's going to be very hard to resolve. For me, part of what was really interesting in all of this is a distinction not between the four positions that were outlined at the beginning of these presentations, but really between two. One that are like stimulus-committed approaches, that is, people who start with their own pre-selected stimuli and determine which among those maximizes the single unit responses. And there, it seems to me that we're talking about the content of neurons, or what neuronal firing represents is the perceptual features among the pre-selected stimuli to which it's maximally tuned. And one key virtue of these approaches relative to the empirical approach that I'll get to in a second is that it maximizes intelligibility. We're starting with something, we understand how complex images are built out of atomic images, and we've got some sort of pre-theoretic idea of how that's going to happen. On the other hand, there's a data-driven, or what Carlos called the sampling approach, where you evolve brain stimuli selected for their ability to maximize firing rates in single units. And there, the neural firing represents the stimulus type that drives it most, irrespective of whether that gives us anything intelligible that we can hold on to. And the key value here is that it's going to maximize predictive accuracy, or the what I think of as empirical adequacy of the model. I think it's important to note that this isn't devoid. I was going to call this theory, theory-free modeling, but that's of course not true. There's a lot of theory that goes into the stimuli that we're evolving, but it's certainly less committed than the other approaches. In assessing these things, in our discussions today, I've been surprised at the number of words on this list that came out in the discussion. This is a summary list of things that I think are useful for evaluating models in science generally. And I've broken it down into different compartments. There are aesthetic virtues, things like simplicity, elegance, and I put intelligibility there. how pleasing it is to our minds. And then there are things like pragmatic virtues, where here I'm thinking about things like, does it open up new questions? Does it suggest the next experiment? And control. Does this model suggest novel ways of controlling the system? And also just things like how easy it is for us to use this model for various purposes. It might be useful, but not true, for example. Then there are formal virtues, and these are the kinds of things that Ko was talking about. I mean, we of course want our models to not be internally contradictory, but we also want them to be testable and to satisfy basic constraints on scientific knowledge generally. And then there are the empirical virtues, and here we've been emphasizing predictive accuracy and empirical adequacy, but we also might think about, does it fit with what else we know about the brain and what else we know about the world? Generality and scope of the model has definitely come up when we talk about the generalizability of the exportability of these models. And unification, does it solve superficially diverse problems with a single explanatory schema? It seems to me that a lot of what's been up for grabs in this discussion is on intelligibility on the one hand versus predictive accuracy on the other. And that's where I'm going to put my attention. But I don't think that these issues of fertility and control are lurking that far in the background, to be perfectly honest. So the first thing that I want to point out, and this is something I've already said, is that you can have perfectly good predictive models that don't explain anything at all. Here's a famous kind of trigonometry problem that people often solve when they're getting started on these things, where you predict the length of the shadow on the basis of the height of the flagpole and the angle of the elevation of the sun. And you're given that information, you have to solve the problem, and you find out that, what X is based on the value of theta in this case. But of course, you could flip that around, and you could say, you could also predict the height of the flagpole based on the length of the shadow and the angle of the elevation of the sun. But presumably the first case was one where we were getting at the explanation. In the second case, we're making a prediction, and it's an accurate prediction, but it doesn't put things in the right way. And this emphasizes, I think, what Ed was saying, that explanation is knowing about how things work, how the brain works. And by that, I mean what causes what and why, or what causes what and how would be a better way of putting it. And I think causal information here is also necessary for control. I don't think that the government, Jack, is paying us to make predictions alone. I think it's paying us to cure diseases and to correct blindness and to correct developmental disorders. And if you only have predictive information but not causal information, you're not going to be in a position to control the situation. We can't control the length of the height of the flagpole by changing the length of the shadow by, for instance, bending the earth or something. All right. And if you want to know what I think causation is, I said something very quickly, but it's in a slogan, it's what you detect with a well-controlled causal experiment, where you wiggle some variable like X and you see whether Y wiggles as a result when you've controlled for all of the other ways that your intervention might have been wiggling X and might influence the effect of Y. We can talk about that if you want. I agree with Code that this is a special subclass of predictions. What we want to do is make predictions about what will happen under conditions when we intervene on the system, but that gives us a special kind of knowledge about what knobs and buttons can be used to control the way the system operates, rather than merely to predict how it will behave. All right. That's another question, and part of the reason why this is relevant is we might ask the question, which predictions count? I'm not sure I'm right about any of this, but it was one thing that occurred to me while I was reading these papers. Does the fact that we can evolve stimuli that maximize neural responses indicate that these are the stimuli that drive the neurons physiologically and ecologically? If we put pressure on the eyeball, might that deliver a stronger response by the optic nerve than visual stimuli would? If we devise fentanyl, we might be able to drive opioid receptors much more than they would be driven under normal conditions, but that doesn't suggest that that's what opioid receptors do, or that the eyeball has been evolved for the purposes of detecting touch. So that's one set of questions, I suppose. And secondly, does predicting neural responses indicate that you understand how the inputs are translated into behavioral outputs? Are we predicting in the right way? And here, Gabriel's discussion of adversarial examples seems to me to be apt. Are we in fact making the prediction on the right basis that will allow us to understand how the system can be controlled? I thought as a kind of, there's another set of issues about these DCNNs, it seems to me, which is how do they predict the neural responses? They make the right predictions, but do we understand at all why and how they make them? And I think this is a general problem in AI these days, where you can build these systems, but you don't understand really what they're doing internally. And yes, you can understand them piece by piece, but do you have any abstract understanding of how the DCNN is functioning? And I was thinking that, we might compare it to a sort of empirical oracle here at Delphi. You ask it factual questions about neural responses, and it always gives you exactly the right answer, but it doesn't tell you why that's the right answer. It just tells you the right answer. And that would be a case where you have sort of pure prediction, but without explanation. And then the question is, would we be satisfied if science was nothing better than this Delphic oracle giving us true predictions all the time? And that's meant to put some pressure on the idea that we can do all of this without caring about explanation or intelligibility at all. Now, part of the reason why I got involved in this was Carlos called me up and said he was getting these reviews for his papers and his grant proposals that said his work wasn't mechanistic enough. And he said, what in the world does that possibly mean? And that's a discussion that's been going on in the chat section. And I think just listening to you guys, that part of what you mean is give me an intelligible model for how the brain works. And does your work, in fact, give us that? And or in other words, tell me in virtue of what your predictions turn out to be right. And when we've got circles and angles and faces that are natural images, there we can make some sense of what's going on. But if I tell you how to combine these evolved images, or what sort of system integrates these evolved images and how these evolved images are processed, I don't have nearly as clear a story as Hubel and Wiesel had about how moving through stages of processing in the visual system lead to complex representations of objects. I'm reminded here, I have to say, of Galileo's claim that the language of the book of nature is written in the language of mathematics. And he says, and its characters are triangles, circles, and other geometrical figures, and without which it is humanly impossible to understand a single word of it. Without these, one wanders in a dark labyrinth. And I thought that echoed in some ways some of the approaches that, for instance, Ed has been taking, or that Anitha have been taking, using these kinds of angles and curves as a basic starting place. But then again, I need to take that back at some level. The world might not cooperate with our tiny brains. These are experiments done by Mary Haggerty, and it turns out that in the one on the bottom left here, we're very good at predicting how the last wheel will turn on the basis of the first wheel turning. But in the other two on the right-hand side, we're really bad at predicting how A will turn at the top when you turn that crank, or how whether the thing will move in the direction of A or a B when you rotate the smaller wheel in the bottom one. Our brains are just bad at assimilating this kind of stuff and making sense of it. And so we might not choose our own intellectual reaction to these things as the be-all, end-all of our model choice. Furthermore, as has come up in the discussion section several times, sometimes we have to learn to give up intelligible explanations. I think Galileo, for example, had to convince people that things do not fall according to their weights. That Galileo had to get people to accept the idea of inertial motion, which seemed exactly backwards and incomprehensible to people, and people had to learn how to find things intelligible that way. And magnets still, I find baffling, magnets. Sometimes we might have to accept an explanation that it's, at least at first pass, utterly unintelligible to us. And I think physics has demonstrated some cases where that seems to be the case. Schrodinger's cat and the Lorentz contractions and the kinds of things that go on in the Einstein-Podolsky-Rosen experiment, the chances that aren't explainable by hidden variables, for example, are baffling to the human mind. And people like Immanuel Kant said that the world couldn't be like that because it would be unintelligible. Well, it might be that we have to learn how to find the world intelligible. And I guess there's a question, and Co brought this up, are DCNNs and the language that we use to describe them like this? Do we have to learn to accept, for example, that convolution is an explanatory primitive? And once we get comfortable with that, we will stop looking for our circles and our triangles and our angles. We'll just be okay with saying, well, just was one of these things operating the way one of these things operates. Nonetheless, I do want to go back on myself one more time and say there are some advantages to having intelligible models. One is just the intellectual satisfaction. You might think part of why we're doing science is because we want to understand stuff, not merely make predictions about it, but to get the intellectual satisfaction that comes with that. But in addition, it seems to me that intelligible models guide the next experiment and suggest ways to extend the model in ways that unintelligible models do not. And furthermore, that intelligible models might suggest plausible and convincing ways to try to control the system. And if that's what we're really aiming at, then having an intelligible model might help us. So I've talked about how techniques and models interact. I've tried to point out that prediction is not always explanation. I've also tried to point out that not all explanations are actually intelligible. We might have to learn how to find them intelligible, but I've tried to give a case that intelligible explanations have some advantages that are worth considering. And I hope that that brings out some of the things that are up for discussion here.
So beautifully expressed, and what a great comprehensive summary of everything that's been said. I wonder, and I don't know whether this is a question for Carl or for everybody else, how could we incorporate this level of thinking into the next year? How about
one thing that has struck me in the discussions is that there is a group in a subgroup here that seems to think that that prediction is everything, and that we'll just decide the model that makes the right predictions all the time. But that seems to me to be not obvious, and okay, certainly up for discussion here. Yeah, go ahead.
And since I keep getting attacked on this, let me explain why I think there is an apparent difference here. The pool that I swim in is different than the pool you swim in. The pool that I swim in consists of journals that do not require anybody to report predictions of anything. They only require statistical significance, and all models are adjudicated based on statistical significance, which is a logical impossibility. You cannot adjudicate models based on the fact that they're non-random. It doesn't make sense to ask which model is less non-random than another model. That is not a logical, but that's the world I live in, okay? And that's the world we all experimentalists live in. Nobody's required to have separate fit and test data sets. Nobody's required to report effect size. Nobody's required to report prediction accuracy. It is a shit show, frankly. It's horrible. It's a horrible, horrible, dysfunctional, like social dystopia that where basically this metric, this 1930s idea of nobody's doing anything, let's do statistical significance as one of the 10 things we should do, has turned into the thing that everybody does and the only thing that is required. So I actually agree with your future goals, but we are so far from there in this field. We're like, so my view is like, let's just get people to do the easy things. Everybody should have separate fit and test data sets to keep from overfitting and to minimize type 1 error. Everybody should have that, obviously. Even if you're doing a damn ANOVA experiment, ANOVA is a regression model. You can still have separate fit and test data sets. In all of psychology, the millions of labs that use ANOVA, there's one lab that does that. Exactly one. And so, nobody's required to report effect size. Like nobody's required to report prediction accuracy. None of this stuff even gets done. So I'm not thinking about what is the ideal thing to do. I'm just thinking, how can we make things just a little bit better before I'm dead? That's why I focus on prediction, and that's why I think it's important.
So that seemed like a brilliant non sequitur to me. I think you have been falsely accused of being obsessed with prediction, Jack, given that from the very start, I think you but with the term elegance, you were saying that intelligibility was desirable, at least. I'm not so pessimistic as you, and I feel like this GAC is a chance to save and nurture intelligibility in our field. And I would also say that people are not, in our field, are not as immune to the idea of intelligibility as you are. And potentially Carlos's experience with study sections reflects that. You know, if people are saying, this isn't mechanistic enough, then maybe they mean, I don't understand what you're going to learn. So I was quite serious in my question of how can we sort of officially or formally incorporate the kind of thinking that Carl is presenting, that I think is so central to everything we've been talking about today, rather than just letting it pass and go off on the next CNN. Yeah.
No, go ahead. Sorry, Ed.
Go ahead, Ko.
Oh, so I actually wanted to understand something from Carl and Ed and others, which is like, I'm really failing. Maybe I am the person who would say, like, right now, at least, that prediction is the end of everything, because I'm really struggling to find examples where there are objective ways of getting to some intelligibility definition, which does not rely fundamentally on some kind of prediction at the end of the day. I think everything at the end of the day, if it can be tested, will rely on some form of prediction. And it's just that we are not defining that particular predictive regime, and that's why we are saying it's something else. But at the end of the day, I think if we understand anything, and if we make it intelligible to any agent, cognitive agent, it has to bear out in some kind of prediction-based task. Is that completely off?
No, Ko, I think that's exactly right. All of this is going to, so intelligibility, I do think is a question about how fit it is to our cognitive abilities, which are of course plastic and can be learned and developed. And so that was part of the point at the end. But I do think that separating out the causal predictions from the non-causal predictions is something that we're already well suited to do, and we understand perfectly well how to do the kinds of experiments that would be required to do that. And it is predictive. It's just not. There are predictions that you make from barometers to storms, and then there are predictions that you make from barometric pressure to storms, and those are just two different kinds of predictions.
Okay, then then it's not against prediction per se. It's just like the level of understanding and the level of prediction, which I think that I totally agree with that. Yeah,
putting things in a causal sequence is part of rendering them intelligible, and so that's why. And if you think that causation is objective, which I do, and you think that what's causally relevant to what is an objective experimental matter, then I think that these are testable questions.
But every experiment is causal in the purest sense of causation. Just like you cannot do any experiment without making any causal interference to the system. So in the strictest of definition, there are no non-causal experiments. Like even showing an image to a monkey is a causal experiment in some sense.
I mean, an experiment that's designed to test whether a variable X is a cause of a variable Y. Yeah. Whether a variable X makes a difference to a variable Y. There are lots of experiments that don't do that, of course. And the causal ones are the ones that do that. You might just be interested in sussing out correlations in the world, or and not caring about testing. Yeah, but sure, like you put somebody in a scanner and you give them a task, and then you watch what area the brain lights up. You're really looking at a causal relationship between the stimulus and the brain activity. That is causal. But the question is, which causes are you paying attention to here? There's this other question, like, is that brain activation actually relevant to behavior? And that when people say that, and I think similarly with single unit recording, there's a question that arises of this sort.
Okay, let's move on to the last part. We're running a little late, but I'm excited about this last section about experiments. And I think Will, Binxu, and Martin are taking over here.
I'm going to try sharing the slides, and Martin will start.
So we're going to try to outline a sort of a practical way forward, at least in the context of the GSC. Just gonna wait for Will. Yeah, go ahead. And so I would argue that, and I think this has come up repeatedly today, that a lot of what has been happening in neuroscience is that we record isolated data from some brain region. Let's say someone records from V1, then we build a model that predicts that data well. Maybe we don't even do cross-validation, but let's say we do. I think that's still a problem that, let's say someone else collects data from IT now. It's again isolated data, and again, we build another isolated model. So eventually you're left with this scatter of a lot of data that is disconnected and a lot of models that are disconnected. We don't know which model is really best because they're all only tested on one particular data. I think Ed said this before, so we're somewhat in this extreme where we're all feeling parts of the elephant. Nobody really knows what the big picture of the elephant is. So this is all necessary, and these are very necessary first steps, but I think it is time somewhat for our field to move beyond that and to really try and build unified models that integrate over a lot of different data. So yeah, testing models is great, but it's insufficient in that one data set alone, I think, cannot tell us the answer. But we just don't have the experimental power to connect enough, even within one lab. So really what I think we ought to do is to move towards what we call integrative benchmark, which means consider all data, really all past, present, and future data together, put all of that to bear on models and build models that predict not just one of those data, but rather all the data together and really generalize to all future data. I think eventually when we impose enough data on those models, then eventually the right models will generalize to new recordings as well. We have one resource of this called BrainScore. We do this for already collected data. And the idea for this GSC now is to do this in a more online and active setting. So really the question, I guess, is what is the right elephant here for the ventral stream? And I think we probably cannot agree on what the satisfying understanding is. We all have slightly different views of what exactly it might be. But at least in Carlos's words, we owe each other the empirical testing of alternative hypotheses. So the GSC, or the proposal in this GSC that Will in a second is going to detail a bit more, is with respect to images, compare who can best drive neural responses in different neurons, and who can drive that activity by generating the right stimuli. And the proposal is to evaluate different candidates on how strongly they can drive single neurons as well as neural populations. I think even though we might not agree on which of those methods is most satisfying in terms of understanding, at least we can empirically compare which one is the most accurate under those measures.
And I just want to give an overview of, well, what we thought we could do. But first and foremost, I guess, in terms of the concrete outcome, I think it is much more important that we get a data set where different theories can be compared to each other side by side. And secondary to that is our metric of driving like a single neuron or a neuron population, because people can have legit objections, and I have my own doubts about how much we know from a stimulus that maximally drives a neuron. But I think with a data set that has all the theories compared to side by side, we can ask different questions and actually test these theories, either in terms of, say, explaining responses to arbitrary, more diverse stimuli that they're used to explaining, and also, for example, like on top of that, whether one theory is more interpretable than the other, more intelligible than the other. And so that's the general idea. Something happened to my presentation. Okay, so one example of such an experiment is something I already did in collaboration with Puya Bashivan from the DiCarlo lab, where we tested the evolution method and the neuropopulation control method side by side in the same neurons. And this is just to serve as an example of what it matters to test images on the same neurons, because so here I'm showing example responses from each grouping is one neuron, and we have 3 types of images. On the right side are substitute model-based synthetic image, so similar to Puya's work, Puya and Ko's work. And in the middle are evolved images for the same neuron. And on the left are the maximally activating natural images. So I think like it's easy to see how each individual camp doesn't fully explain all the other alternative possible stimuli, like a person who says that, oh, maybe this is a monkey face responsive neuron, a categorical view, will not be able to explain why these kind of very garbled images also drive this face neuron highly. And obviously the evolution viewpoint will not be able to explain why it came up with this particular image and not that image, which in some cases, like the image found by one method is better than the other. So why didn't the evolution approach find such an image? It may not be surprising, like in principle, because we all know that testing any of these finite set of images is an imperfect approach. But I think what we lack right now in the field is a comparable data set where these can be tested against each other. So, and just to illustrate one utility of such a data set, here the metric is focused on how well model can generalize, and Gabriel already showed you this plot. So if we have stimuli that are actually vastly different in style, we can divide out true test sets and then really show how the predictive models fall short. I'm going to skip over this UMAP. Well, just quickly, the UMAP visualization is meant to represent how a neural population represents these different categories of images and how a CNN represents them. And with this, it might be not surprising that a CNN fitted on, say, natural images may have a very good linear fit in this region, but that linear fit can extrapolate very poorly because now your test set is very far away from the training domain. So, okay, and I think that really is most of what I wanted to say. I'm going to skip over exact metrics because I don't think we can fully agree on what metric is the single one that will differentiate which viewpoint is the better. But I think the useful concrete outcome is we can collect a single data set with different viewpoints that at least all have traction on the same data set. And the approach we propose of doing that is, I think it's pretty important for this purpose to use chronic recordings because, as many of you have mentioned, neuroscience is data limited right now. And chronic recordings just allow us to both fit each theory on the neuron and to test the theory in a as close as possible recording. And this is important here as a future experiment proposal because, of course, the literature already contains testing of different theories on different populations of neurons, sometimes in the same brain region, but the same brain region could also be slightly different recording locations. So it's never really satisfactory for comparing theories directly. And I think we need an experiment where these viewpoints, theories, or stimuli are tested on the same neurons as much as possible. I think I will leave this for discussion. Like concretely, how do we choose what stimulus to test? And maybe that will depend on how we plan to evaluate them, but maybe not.
Could I make a comment? Will?
Yeah.
I would say, recording quality would be really important as well, being highly conservative in terms of if you decide you want to study single neurons, being highly selective in your choice of in your spike sorting criteria would be critical because contamination from nearby neurons in areas where you don't know that nearby neurons have similar tuning properties. I think that would influence the conclusions you draw. I think that's a important criteria to think about.
Yeah, that's fair. With chronic recordings, I guess you can always have metrics and then like on a continuum rate, how good each channel, each sorted unit is, right? Like a standard approach is to have a fingerprinting set across days. And of course, you can compare waveforms across days. There are established ways to do that. But
right, yeah. So the question is whether you're, even with your fingerprinting set, whether you're recording from a single neuron or a multi-unit population.
right, yes. So you know, there's also waveform comparison across days.
That's right. I'm saying that there are criteria, there are thresholds you set, and being more conservative would yield better single neuron quality. That's what you want.
I agree with you, Anitha. The problem is on Jim DiCarlo's lab's done the fingerprinting method, and my lab's done the fingerprinting method, and there's no published like algorithms on it. So yeah. If I was a user who hadn't used this method, I would be very concerned, and I think that's perfectly legitimate. And I should also mention that although I'm also a believer in the fingerprint method, because I think Jim's lab and my lab basically invented it in parallel, and I think it works well, it is very labor intensive to make sure everything's right. You have to go through every single damn neuron by hand and check them, and it's a giant soul-sucking pain in the butt.
That's right. And if you want good data,
you have to do it.
Can I just point out that David Leopold's experiments with Bondar electrodes, I think, are great examples of effective use of fingerprinting with 200 stimuli to establish statistically that you're looking at the same neurons across weeks or even months.
Oh, that's right. I forgot David was doing that now too. Yeah, right.
Yeah.
This goes back to 2016.
Yeah.
All I'm saying is you could use the methods to set your thresholds high or low, and depending on that, your data quality depends on the thresholds you set.
Can we talk about data quality as being equivalent to single unit? I mean, ultimately, and this is a part that was kind of skipped that because of time, but ultimately we want to explain populations, we want to explain even multi-unit activity, collections of multi-units and single units, not just single neurons. So
let me clarify that yes, populations, but populations of single neurons. There's a difference between populations of single neurons and multi-unit activity.
Even in a
you can always go up,
cortex?
but you can't go down. If you collect single units, you can build a model that will integrate them into an MUA, for example. But if you're just recording multi-unit, you never get the single units. So
yeah, but again,
it's always easier to go up.
Again, that importance matters, right? In that, you can find, and it's been tested. This has been examined by Bill Newsom and many other folks, that you can record from a single unit in a given electrode and then characterize it along multiple functional dimensions, and then also see how the multi-unit around that single unit behaves. And they often find that it's exactly the same. Again, this is a benefit of the cortical column. So
yes, but Carlos, that's after they very carefully position the electrode in the center of the column. That's how they did the stimulation experiment.
And yeah, the question is whether you know the size of your column, how they're clustered, whether it's a column, whether it's a patch, what it is. And you can imagine that downstream neurons are looking at multiple single units and that's different from collecting multi-unit data.
There's also theoretical work that point out that at least for certain tasks, if we look at few enough task variables, looking at multi-unit activity is equivalent to looking at projections of a single neuron population. And basically the conclusions never change. But I totally see that single unit precedes like multi-unit activity. You can go one way and not the other. So yeah, to the extent we have well-isolated single units, of course, those will be like the gold standard.
Yeah, you should have them. But basically, if your output measure doesn't seem to care across either one, then it's a question of one hypothesis of what the decoder is doing at the end of this data spike collection.
one thing I think also Thomas asked this question as a bomb throw, like why single multi-unit, why not 2-photon calcium microscopy, large populations, or fMRI, whole systems coverage. I think I briefly mentioned my opinion on this was like, I think we should start from a behavior of choice and first figure out at what level of the signal that we are measuring do we have full behavioral predictivity, and that makes the rationale for me to then go ahead and explain that particular neural property, whether it's single unit, multi-unit, that at least grounds it for me, and that's the approach that I want to pursue. But I don't know what you because like, of course, that we can go to single channel, but then we can go to like channel opening level. We can do like a lot of stuff that is not currently done.
Sure,
but
it's your choice.
Exactly.
Yep. And I would say 2P at this point, it's a time course thing. You know, single neuron spiking, you can present stimuli for 200 milliseconds and you can collect the data, and you don't need to have anesthetize animals.
But I was wondering whether there are certain behaviors.
I think
where
I appreciate the point. I think it's important, but is this an important and critical decision right now, or I mean, it's a question about what kind of a lex we the field want to use, or can we agree that we're going to do multi-electron recordings and then everybody can do spike sorting? We can even compare the spike sorting methods if needed. I guess what's the decision question right now? That's
no, I meant it only as a small comment. I did not mean to take the discussion in this direction. Sorry, discuss this direction.
Yeah, I guess to follow up.
I think important point. So then I suggest that I mean that there are so many other fundamental issues to decide. I'd like to decide urgently now. I suspect this is anyway.
Yeah, to go off Gabriel's point, I think the key here is, based on my understanding of the presentations, I think it is valuable to have a data set to compare these different viewpoints. But am I misunderstanding that maybe people think it's sufficient to compare populations in separate papers that each test their own stimulus set? Is that enough to like synthesize and compare models to each other? Yeah.
So, Will, my answer to that would be at least a partial yes. And I would offer your one of your examples in a few slides ago in proof. So the example I have in mind is the one where the high response natural images are monkeys looking down. And maybe you've realized this, but the high response images generated by Xstream all have two black spots in a white field, and the two black spots are decidedly low, which is the case. So that just seems like an example right there of a single data set that is amenable to two kinds of interpretation, the second one being a structural one. I'm not saying everything can work that way, but.
Right, and I think that's fair. I mean, in that design, it was already intentionally including at least 3 different types of stimuli, right? So are you saying that that's enough, or like, is it worth us coming together to design an experiment where we pull the stimulus, like we all think might be interesting, into one experiment?
Yeah.
I would like to point out that you don't have to design the same experiment. You only need the same test set. In principle, anybody can do anything they want. It's just like the issue of how you validate a model on natural images. You validate on natural movies or images, but you can build the model on anything. And the same thing goes here. We just need a common test set where everybody can use that test set, and then they'll be able to compare predictions across labs no matter how they collected their data. That's a way lower bar and makes it way easier for everybody.
Yeah, I like that idea. Everybody pitches in, and so I think it's important because, as been pointed out before, these neurons can respond very differently across the photographic images versus computer generated. I think it's important to get a sense of the response range of individual neurons, and as well the behaviors that that populations actually exhibit. So here the question is predictions is, let's say that we all have the same test set. Are we asking who can predict the responses of neurons to this test set of individual neurons or neuronal populations, and have the best match in terms of firing rate, and or an explanation of why that is?
I would say both. Per Carl's talk, we can compare metric predictions. We can at least discuss relative intuitive explanatory value. Two thumbs up to what Jack is saying. I think multiple labs can study different neurons with related stimuli, and Will and Binxu and I were talking about this a meeting or two ago, and specifically the idea of coming up with category stimuli like coffee mugs and hammers and things like that. I was pushing for doing that with virtual stimuli, for which we have all the ground truth that you would need, even for 3D structural models, which I would like to do. Virtual stimuli can be beautifully photorealistic now. It would give us a common data set if we had 100 or 200 objects like this. I think one of you two guys pointed out the idea of making sure that the spectral statistics, any other measures you can think of, are equivalent to natural photographs. But it would give us a data set that we could all use that doesn't take that long to show 200 things, and then people can show whatever else they want in order to try to model what leads to those responses, and they can do whatever analyses they want.
I completely agree with what Ed just said. That's easily done in Blender, and you can get all the ground truth out. One of my old students did exactly that in an MRI experiment. It works really well. You might also consider throwing in like a standard natural. I would advocate for a standard natural video in addition to that. But I definitely think that's a good idea.
Yeah. So everybody can put in the thought their
comment.
Gabriel?
So just to indicate that it's not just the test set. I like the idea of using virtual images for sure, but it's not just the test set, because I think a lot of the proposed models here for certain X3 as well as the computational models need to be predicting images for a given set of neurons. So we cannot just common test set. We need to. That's why this division into day 1 and day 2, where in day 1 we still need to be able to use the same neurons, for example, for evolutions or for some of these computational models.
Granted. To get back to Jack's suggestion, what do you think about virtual video, Jack? Which would offer the same advantages, and
you can do that.
I agree.
In fact, you don't even need to make it. Blender, as part of their, Blender's constantly, it's like amazing and horrible software. It does amazing things. It's horrible to use, and they constantly change it every 6 months. And unless you're an aficionado, it's impossible to keep up with it. But every time they release a new Blender, they release essentially a promo video. Like the last one I remember was the Big Bunny, which was essentially kind of this pseudo animated but realistic video. And you could use something like that. And then you have all the ground truth from that too. So yeah, that's a good idea, Ed.
Good.
I just wouldn't want to make it. A giant pain in the ass to make it, but to get one would be good.
Good. And I would say that in order to really do something with it, we need multiple such videos, because you can't learn that much about from the response to just one stimulus.
Well, so now the issue is now you're at the crux, because the critical issue is how much test data are you going to collect and how long, how much time, right? If you're, for you guys who are doing awake critters, you've got 5-second trials. So how many 5-second trials, right? That's what it all boils down to. And really that's, as always happens in neurophysiology, the rate limiting function isn't what you want to do, it's what you can do. So I think you guys need to decide what you can do.
And it's also noise. I mean, you need multiple presentations because of noise in the response. So it's
right, because you want to get a noise ceiling. You want to get
yeah.
If you're going to calculate a noise ceiling on the test data, you need presentation. You need multiple prets. Yep.
I think we could pull off 100 to 200 unique images or very short
time. Just calculate time, then back calculate how many images you can fit in that time. How much time are you willing to devote to this? That's the issue. How many trials?
I feel like I missed something, and I want to try to get a clarification here. My understanding is that the point of this proposal is that different groups will come up with their own stimuli that drive the same set of, that's not it?
The problem with that is that if everybody comes up with their own stimuli, they could be eliciting different response ranges from neurons. And some of those, it's easier to predict sometimes how neurons will respond if your world is small. So we want to make sure that we have a very, very challenging, very wide, out of domain set of images to really show, not just how.
Sorry, I thought the challenge was just to drive neurons as much as you possibly could.
No, not
What I thought too.
Understood.
To predict patterns. But do you have that slide, Will?
To predict patterns?
Patterns of responses. So it's been pointed out that maximally evoking, maximally stimulating images, that's kind of the tradition in the field. That's how it's been done since Hubel and Wiesel. It's supposed to mark something important about a visual attribute. But in real world, most of the time that the brain is active, most neurons are not being maximally driven. So that means that at some point we need to be able to understand if I present an image, a natural image, and then I'm recording from 100 neurons at the same time. They all have a specific pattern. That pattern of activity contains some information about the visual attributes. Can you predict as a team what those visual attributes are? So somebody that believes in that maybe it's some kind of structural component might create equivalent images that contain all of those information. It'll be a reduced image, and therefore that pattern should be approximated. If somebody says, no, I'm sorry, you need the presence of this semantic object to elicit that, then you should be able to, again, create that.
This does not seem like a scalable idea because there are millions of neurons and there's going to be millions of those images. And at the end, you will have to rely on models that take all of them and then start predicting some neurons, whatever you're recording in whichever monkey. So I think relying on the image space is going to be problematic. I think at the end is going to be some prediction of the models that are going to come out that you have to test. And
no, so I think, we have some data actually of how this can be done using the evolved method. And I thought you guys want to present a little bit of that.
Yeah, that should be like the next slide, but kind of will jump it over. But I agree with Cole that this idea itself is kind of not scalable because there are so many neurons and so many patterns you can test, and not sure get one. You can play the video if you like it.
So could I clarify the idea? The idea would be that you've got 200 naturalistic images for which you have total ground truth. Everybody tests those, and then they can test any other stimuli they want in order to build a model to predict the responses to those. I don't know in what sense that's not scalable, whether you mean that it's not scalable across multiple labs or multiple areas or multiple neurons, but I don't see the problem.
So I think there are like two different objectives. Like Carlos' proposal is kind of see what is the image attribute that drives a certain pattern, which is kind of solving an inverse problem. So in this slide, what I was doing is I select one specific neural pattern, like in the black traces, and we search for images that elicit a certain patterns, like by searching in the neural space, just using the evolution pipelines. And the target image is the apple, and the search image is the thing you see in the middle pattern. So it's like a yellow thing with certain blackish things in it, which elicits the same population response, not same population response, but the correlated patterns with the targets. And it's doable, and we can do it better now. But you can imagine like we do this for each patterns, or like as View has proposed, we may be able to do this with like certain PCs for the population and say this population's this principal components codes for this feature or its attributes, and finding that correspondence may be the target for this study. But I also kind of acknowledge Cole's point that this like takes efforts. It's not like scalable to, I mean, different populations may have different this PCs and different patterns, and it's intensive. Yeah. Also like another proposal or objective another proposal like Connor and others has said is so my understanding of this is what is the best training set, or what is the best sampling strategy we can use to learn about a model, learn about a neuron, and we can all test our model for that neuron on a common testing or validation set. And I think that is also a very interesting problem. And like different labs have different sampling strategies. Like we will use like this kind of evolution or optimization based approach. And like the Caro lab will use their nature images, and make Connor labs will use your Blender-based synthetic images and their parameters to as your training set. And we can kind of all build our model of the neuron. I mean, each for a day of experiment, and then we'll test our own models on the final day's testing set. And I also like that idea as our like competitions. Yeah.
Precisely.
Yeah.
I think that I want to make a decision here. I think that part of the issue is that the test set is not fixed, because several of the approaches, the test set depends on the neuron that you're recording from. So for example, if we want to predict firing rates to X-dream images, we first need to run the X-dream algorithm. Similarly, with a computational model that will generate images, we need to train the model on the exact same neuron and then make predictions. So that's this division into a day one, day two, where we have a set of images that are fixed, and those images could come from virtual images or semantic categories, or a fixed amount of images. Again, as Jack pointed out, the bottleneck is always the amount of time. So we have, let's say, one experimental session for each. We can have the different proposals. But part of the issue of really comparing all the algorithms side by side is that we need to be able to run all the algorithms for the same neuron, right? So we need to be able to run X-dream and the visual model on the same neurons, in addition to a fixed predefined set.
I mean, I guess we could we do like a bracket, like a tournament bracket, where sometimes it's just pairs of approaches on a given neuron, and then just have overlapping sets, and then eventually infer something from that. Like, yeah, even going from the day one to day two thing is concerning to me, in that, you know, single neurons sometimes go away, right, from day to day.
I don't understand the day one, day
So this approach, day one to day two, assumes that the single neurons did go away, and also that they're starting the same neuron. So that's an important assumption that may be great. I think the pairs of options is a possible way to go. I think it would be limiting in that we really want to basically, as I pointed out before, let the flowers bloom and compare all different ideas by side. So we're limited to pairwise comparisons. I think it's forward, but it would be nice to be able to pair everything at the same time.
I'm not sure we're talking about the same thing.
Yeah, me too.
I think what Binxu is saying and what I'm saying is you've got leave aside video now, granted it has problems, but you've got 200 naturalistic Blender generated images of different kinds of things, and everybody studies those, and it takes them 10 minutes to run 5 repetitions of each. And then they do anything else they want to test and analyze the neurons that they have online that day. I don't think that has any serious practical impossibilities.
The only thing I would disagree with there is
I think that would be very cool, but I think that would not be testing all of the ideas that we have discussed here. For example, here's one thing that we want to do. I may want to take the same neuron, build a computational model of the neuron, and make predictions about novel type of images. That's what Kohn and others did in their science paper. That's not included in the version that you just alluded to. Other thing that one would like to do is take the same neuron, run the extreme algorithm, and then test all the same neurons on the same extreme images. And that's the paper that Carlos and others published also in 2009. I think those two would not be included in the kind of approach that you're describing.
So Gabriel, just to add to the point, so I think you are concerning about like the extreme or like the closed deep control system is kind of cheating because it's like proposing things based on the training set, and it can use those kind of images to challenge others. So like one thing we can think about to accommodate or reconcile this is like each way of fitting a model or to propose images, you get your top extreme images and then add those images to your validation set. And you can use these images to challenge other models. Like our evolution system can propose some extreme images. And I think at corner, your methods can also be optimized and produce some sort of like extreme images based on the parameters. And then you can add that to your validation set. And also the deep control system can also do that. And then we compare the validation predictions on the classic like validation and this extreme validation, which may be better.
But even more directly, Will, I would say that we could do what I think you just proposed. That is, you've got these 200 images. You run extreme, get high response synthetic images, and then you make a prediction about which of the 200 images you're going to get a response to based on similarity measures to the extreme results.
That I think that is like similar to what day 2 here like is referring to. Every model is required to test all the stimuli. And you're just specifically focusing on like the 200 natural images. But for extreme, at least to do that, you need like additional time for the algorithm to work with the neuron, right? That's what day 1 is for. I think day 1 is for fitting each theory, each model onto the particular neurons being studied. The fitting set depends, for some of the methods, depends on like the images.
So I would imagine that each lab has a different procedure with different fitting sets. And the question is, how well can you predict the responses to the 200 shared images, right?
That would be one way to do that, yeah. Then the fitting set will not, the testing set will not be particular to the neuron, but certainly.
Yeah, I think that way the testing set is nice, not to the neuron, and then we cannot test the leading models. We cannot test the presence from the computational models. We cannot test the extreme predictions in that.
And anybody can do any test they want in order to fit the model, but the out-of-domain verification is the shared 200.
Yes, listen to Ed. Ed is right.
Yeah, I like that.
I like that too.
God, I wish I'd taped that.
This is taped, and also we're 37 minutes over time. So here's the question: is what we owe the audience? We still some people left. So are we going to settle on experiments now, or can we just go on and promise the audience that we are going to come up with some exciting experiments they'll be seeing about next year? Should
It
we?
sounds like it remains to be determined.
Yeah, we're gonna have to meet, but we can promise everybody that we are gonna continue our conversations.
Yeah, it's just details left. You guys got most of the way there.
Any questions left from the folks that are still around in the audience? I got one from Mark saying that we're very late.
Well, you will all have an opportunity next year to present your progress, your decisions, and the consequences of those decisions. But yeah, I think now is a good time to wrap up. So on behalf of CCN, I want to thank all of you for participating. It's been awesome. And then this has all been recorded, and you'll have a chance to see the video within the next couple days. It'll be posted. Okay, so thanks again to everyone. I am going to end the session, and
thank you all.
Thank you all.
This was great. Thank you.
bye.
Thanks. Bye-bye.